Hello, everyone, and welcome to SOAP 2020. My name is Christoph Reichenbach, and Paddy Krishnan and I are the PC chairs and hosts for today's SOAP. Our main program starts in about 14 minutes with Peter O'Hearn's keynote, but we thought we'd take some minutes before the main event to introduce the program, discuss some of the changes that we've been making, and give some opportunity to thank all of the people that have been involved in this very unusual SOAP that we're seeing this year. Now, the unusual situation that we find ourselves worldwide forces us to try out new formats and to try other ways in which we can do science, or disseminate our results. And as part of that, we think that it's also a good opportunity to try to experiment with different kinds of things that can enhance or at least alter the way in which we in the future will be doing research or sharing it with everyone worldwide. So this is also an experiment to see how effective and useful it is to do SOAP, which is intended as a workshop, i.e. as a very interactive form, in this video streamed format. So let me start by giving you a brief overview over the program. What we will have today, let me first give a summary of what we're doing for SOAP overall. So this year we had only 5 submissions to SOAP. The submission deadline was very close to the point in time at which the COVID-19 epidemic started to really reach everyone's attention and lockdown started. So it's possible that this was a key factor here. We decided to focus on quality submissions. So we only accepted 3 of the 5. The remaining 2 were promising, but we thought they were a bit early. We were very lucky with 2 excellent keynote speakers, Caitlin Zadowski and Peter O'Hearn, being willing to show their work to us here. And we're very much looking forward to what they have to tell us later. But in addition to the keynotes, we also have a new format, which we haven't tried before at SOAP, to the best of my knowledge, and these are tool talks. The idea in tool talks is that researchers and practitioners from the industry who work on interesting program analysis tools and program analysis related tools come in and give a relatively short talk about what it is that their tools can do, and either focus on some new innovations that they've made to the tool or on some general lessons learned, or just a tutorial on how this kind of tool can be helpful for other researchers in their research. So these tool talks are also an experiment for us now. And we believe that this fits quite well with the free registration online formats that we have here. Another somewhat unusual thing that we have is that the number of registrations for SOAP this year was a total of 2,330, which is about a factor of 50 more than we had originally planned for, which is why we are experimenting with some other kinds of online formats here. So with that, let me give you an overview over the program. So we're currently looking at the welcome session up here, and we will then later at, in 10 minutes, depending on what time zone you're in, it's going to be 12 UTC, have the opportunity to listen to Peter O'Hearn talk about formal reasoning and the hacker way. This will go for about 1 hour with 10 minutes for questions. After that, we will have a break. Then Xi Wu will explain bug provenance with trace witnesses to us. We will have a presentation by Michael Reif from TU Darmstadt on Takai, an intermediate representation based on abstract interpretation. Then Raphael Monard will give us a presentation on value and allocation sensitivities in static Python analyses. Then we'll have another break. And then come our tool talks. Well, the first 4 of our tool talks. Bernard Scholz will present Soufflé, Yannis Maragdakis will present Dupe, and Gabor Marton and Daniel Krupp from Ericsson will present Code Checker, while Christian Kada and Martin Nowak will present CLE. We'll have another break, and then Caitlin Zadowski will join us to give a talk on Beyond Code, New Signals for Static Analysis. We finish up with 4 more tool talks. We've merged 2 of them because they're closely related. First, Eric Bodden and Philipp Schubert giving talks on SUIT and Phasor, and then Lingua Luo giving a talk on Magpie Bridge. And then finally, but certainly not least, Julian Dolby giving a talk on the Walla system. Then we will wrap up and also announce the winner of the Best Presentation Award for this year's SOAP, which will be one of the technical talks, i.e. the research papers. So to participate, we have a, as I said, somewhat different format from how you may be used to it from conferences. What we ask that you do is that if you want to ask someone a question, please go to Slack. Please go to the SOAP channel in Slack. Select the talk that you want to ask a question about, or if you have a general question on SOAP, go to the very last question and post your question there. Click on the this particular message here, so here where it says one reply, this might be more replies by the time that you get there, and ask your question on the right-hand side in the particular thread. This will allow us to keep track of what it is that you're asking about, and will allow us to make sure that during the, well, at the end of the talk, we look at the right place to find questions for every presenter. So we will only ask questions that you have written into your threads, i.e. the presenters will give their talk, then we will go into the Slack, we will look at what you've written into the thread for each of the talks, and we will select questions from there to pass on to the presenters, ask them in the live stream, and you'll be able to hear them react to it. Now, the presenters may also reply in the threads later to give you answers there, either refining the answers that they've previously given or answering questions that we didn't have time to cover earlier. But this is not guaranteed. So I hope that this is a format that will work for us this year. It certainly gives us the opportunity to continue discussions long after the talk is over. That is, you can still keep using this forum for as long as you'd like afterwards. Now, this is for the main SOAP channel. We realize that because this is a workshop, there may be other things that you may want to talk about. Maybe some talk sparks a new idea that you'd like to discuss with some colleagues. And for that, we've created the SOAP Informal channel. And here you can create your own discussion threads. And these discussion threads can be on anything that you think is appropriate. So just go to SOAP Informal and post your thread there and discuss with your colleagues what it is that you'd like to be discussing. So with that, I would like to thank very much all the many people that were involved here. I hope that I haven't forgotten anyone. So I'd like to thank, first off, the program committee, George Palazzouras, Julian Dolby, Jeff Foster, Uday Kidka, Katarina Urban, and Greta Jorsch, for their hard work in taking the submissions that we received, carefully reading and analyzing them and building opinions about them. Also, Julia Laval as our external reviewer, who was very instrumental in one of the reviews. Then the PLDI team, Alastair Donaldson, who is the general chair, Stefan Marr, who is one of the workshops and tutorials co-chairs and was responsible or is responsible for us. And Dan Jorga, who is the student volunteer chair and has been extremely helpful in getting all these online systems set up for us. And of course, all the other SIGPlan and ACM contributors, such as Annabelle Satin, who have made all of this possible for us. And of course, we also want to thank our speakers in advance, Peter O'Hearn, Caitlin Zadowski, Xi Wu, Michael Reif, Raphael Monat, Bernhard Scholz, Yannis Maragdakis, Gabor Marton, Daniel Krupp, Christian Kadar, Martin Nowak, Eric Bodden, Philip Schubert, Lingua Luo, and Julian Dolby. And with that, we have about 3 or 4 minutes until the main talk, well, the first keynote by Peter O'Hearn. And that means that you have another 4 minutes of a break before my co-chair, Paddy Krishnan, will take over and introduce Peter.
Thanks, Christoph. So we'll start exactly on time. It's about in 4 minutes. So people can get a last minute coffee or whatever they are getting in the appropriate time zone.
I'm having trouble getting started here. I'll share screen. Host disabled attendee screen sharing. Try again. No.
Christoph, I think you have to enable screen sharing.
Screen sharing is disabled for me.
I think the host, Christoph, has to enable that. While Christoph is looking into that, I'll do the formal introduction. So thank you very much, Peter, for agreeing to give this keynote. We greatly appreciate that. So for those who do not know Peter, he has more than 25 years of academic experience and I think close to 10 years of industrial experience. He's worked a lot in formal methods and sort of taken the promises of formal methods and applied it to what I call the unruly real world with great success. So actually I'm looking forward to his presentation on sort of the formal methods and the hacker way. So over to you, Peter. Thank you very much again.
Okay, thank you. Right, that's not where I want to go. Okay, Great. Okay, so thanks to Patty and Christoph for inviting me to give this talk. So, I mean, it's a real pleasure to do so in this time, which is a difficult time for many of us. It's like a real pleasure to be able to spend an hour talking about subjects like formal reasoning and program analysis. So I'm really pleased to be able to get to this opportunity to do it. What I'm going to do in this talk is I'm going to start not very technical, and then we're going to get a little bit more technical, and then we're going to get very technical right near the end. We're not going to start too fast on the technical side, but I want to talk about some of the human side of doing program analysis in industry. So let's begin with the hacker way. So the hacker way actually is an address nowadays. It's an address where the Facebook headquarters are located in California. Now, if we go forward, and so I'm not here to talk about the address itself, but rather what happened to me when I arrived there. And so I arrived there because back in 2013, there was a small startup company called Menoidics, and it was acquired by Facebook, and I joined Facebook as a result of this. Now there's the leadership team of Menoidics, which is myself and Dino Di Stefano and Cristiano Calcagno, and our CEO, B. Lavender. That's our people there when we visited Facebook just before the acquisition. And at this point, it was pretty clear that they were going to make an offer to us, and we were going to have an offer, and we were going to join the company. Now, you can see that Cristiano and Dino and B are looking very happy in this picture. I'm perhaps not looking completely happy. Now, you wonder why that is.
Sorry, Peter, I
Yes.
think you're sharing the wrong screen. We can't see any pictures. Sorry.
Uh-oh. Oh, God. Okay, I'll just do escape. Okay, I see this. So let me go back to Zoom. Here's Zoom. I see, and now I want to share. I'm going to stop the share. And I'm back to Zoom. I want to screen share. Share. Do you see the hacker way now?
Yes, that's perfect. Thank you, Peter.
Okay, folks. Okay, I'll get back to there. So yeah, a little bit of a hiccup there as we get going. So I'm going to start not completely technical, and we're going to get more technical as we go along. So there is the Facebook office at Hacker Way, and there, as I was just talking about, is Cristiano, B, Dino, and myself just before there was an offer for our company, which we accepted. So then we ended up joining Facebook. And I'm not looking completely convinced, maybe in this picture, people have said to me, where they look very happy. Now, why is that? So when we got to the campus, we saw things like there's hack emblazoned on the pavement on the Facebook campus. And besides that, there were posters on the walls like move fast and break things. What would you do if you aren't afraid? The foolish wait. Done is better than perfect. There were culture posters on the walls like this. And here I had spent 25 years in academia on the subjects of mathematical logic and program verification, very slow subjects. And I was getting pretty nervous. I was thinking, oh my God, is this going to work? Can this possibly work? Taking formal reasoning technology into this setting. Now, okay, when I joined the company, I didn't get any more confident, and it wasn't for those reasons. I was really enjoying myself. It was because of what I encountered. So I encountered lots and lots of code. This is back in 2014, well over many tens of millions of lines of code in the company. And not only was there lots of code, but it was changing extremely rapidly. You see more than 100,000 commits per week. So not only have we got big code, there's huge momentum, changing rapidly. How am I going to take formal reasoning, one of the slowest paced things, move slow and break almost nothing, to work in this situation? Again, well, it wasn't obvious that this was going to work at all. So then we kept going. Luckily, In 2009, in the POPL, we had made a version of what's called a shape analysis, which is one of the more expensive program analyses, trying to get a picture of the data structures in memory. But because we had made it compositional, it was able to scale and at least get some answers on large code. So we could deal with the millions of lines of code in the Linux kernel, and we could deal with the tens of millions of lines of code at Facebook. Previously, it would have been difficult to deal with 1,000 lines in the whole program analysis. So that was good. So once we got into the company, we wired up the program analyzer we had, which was called Infer, and we got it running on the Android code bases, which were several millions of lines of code. And then we trained the analyzer on the Android code base. So we trained it, tried to get rid of false positives, and tried to get good results, so that we thought that there was a low false positive rate. So we worked at this for a few months. Then we switched on the analyzer and we ran it nightly on this millions of lines of code base, and we shipped bug lists to the programmers. And then something really strange happened. We were greeted not by, they didn't congratulate us, we were greeted with silence. They didn't fix hardly any of the bugs, or I'll say none of the bugs, unless we cajoled them really strongly, then perhaps they would pay attention to a bug. Now, this for me just reinforced the fear that I had earlier. So here we were, we brought this technology in and the developers weren't paying attention. And I was wondering, like, is this going to work? Am I gonna have to go back to university with my tail between my legs because this doesn't work? And I wasn't sure, but as it is, you keep going, you keep trying to do things, but this caused a few sleepless nights, but I was still trying very hard with the rest of my team. Yeah.
Peter,
sorry to interrupt you, Peter. Again, I don't think the slideshow is actually playing. It's still stuck on the first slide.
Oh my God.
Sorry about that.
Yeah. Can you advise me how to fix this? Can you see, you don't see batch mode?
Now I see batch mode, but previously it was stuck on that hacker way and that was it.
I see. So when I do slideshow, it doesn't work. So I'll have to do it in a different way. So if I do play, now I'm going to go forward one slide. It's not going forward one slide? No?
correct. Still on deployment model now.
Yeah, still on batch deployment mode, yes.
Well, that's very interesting. You know what? I'll do it in a more ad hoc way. I'll just do it.
Yep. Thank you, Peter.
Yes, yes. So here we are with the batch deployment model. So there we skipped over the hundreds of millions of lines of code, the compositional program analysis. Now we're on the batch deployment model that didn't really work. So that didn't work very well. Now, just let me check. You see 10 plus million lines of code now, yes?
Yes. Okay.
So, so although this batch deployment model didn't work very well, at the next step, in parallel, what we were doing is we made use of Infer's compositional capability. And that's, there's many commits being put into the code base each week or each day. At any given time, there can be thousands of commits on the fly. We wanted to make use of the compositional nature of Infer to process just the commits, or just the commits plus some cached surroundings, rather than the whole entire code base. And so the way they did this will be the only bit of separation logic, that theory that we'll see in this talk, is that separation logic has a way to make sure that when you're reasoning about part of a program, you only need to look at the part of memory that it touches. And this involves something called the frame rule. So what was happening is that Infer, many instances of Infer were running on this large code base. And each instance would look at the bit being changed by the commit, and it would pick off just enough memory, modulo some things about abstraction, pick off just enough memory to analyze that commit. So at any given time, there were many copies of Infer running, doing little bits of local reasoning on different parts of the code base. And so it turned out this was far beyond the scale of anything we had encountered when we were working on this in the academic subject. But it turned out that this was working. It was working in the sense that it was getting answers. Now, then came a big surprise. What this compositional deployment model, based on the incremental local reasoning, fits with is a setup where what we do is we analyze programs at diff time rather than by a batch mode. So the diff time deployment means this. So a developer submits a diff, and it means a code mod, and an instance of infer is sparked up in the CI system and it runs. Now, if infer finds a new bug in the code base caused by this diff, not an old bug, then it reports that new bug on like a social media for coders called Fabricator. This is where the code review happens at Facebook. So the code review is happening, so the human code reviewers and the tool are working together as participants. So the tool submits a bug report at the same time or in a similar time that the human code reviewers are discussing the code change, and then eventually the code makes it to product. So this is, I would call it continuous diff time, to contrast it with the batch mode. Now, so what infer does, it automatically writes comments on code like this for the programmers to look at and the people to discuss. Now, the amazing thing that happened here, which completely was surprising to me, is that whereas the batch mode deployment was 0% fix rate is what I'll call it, since we found batch modes that are better than 0%, but then it was 0%. The diff time continuous fix rate, the rate at which the developers fixed these bug reports, was 70%. Note that's for the same analysis with the same false positive rate, we get that much of a fix rate. To me, this was stunning. One of the reasons the developers explained to me is that when you're commenting at code review time, the programmer's mental context is switched in, and the batch mode deployment asks them to change mental context, which is very expensive. That and other reasons were the explanations as to why the diff time continuous was better. But it suggested to me something that maybe the most important thing in program analysis is not necessarily the false positive rate. And it would be nice in our scientific studies if we had different measures. Rather, the measures that we use in our scientific studies are as if batch mode. You get lists of things, you get false positive rates that the humans judge, and you get a timing. It would be great if we could get ways to measure the analyses in scientific papers that spoke more to the speed and the turnaround and the way of interacting with the developer, like I'm talking about here. So this was quite a powerful experience. And when I step back and I think about it, is the higher level reason for why this worked is that we've integrated with the programmer workflow. We've integrated with the way that programmers work, rather than asking programmers to integrate with the way the static analyzer worked. And Zuckerberg put it like this when he, in his letter to investors in 2002, he said, "The hacker way is an approach to building that involves continuous improvement and iteration." So you see that what the programming model is based on iteration. So fast iteration by sending diffs into the code base. And what the program analysis did is it sat alongside the programmers, taking serious this way of building software. When we sat alongside the programmers, when we made the text sit alongside the programmers, then all of a sudden it performed much better as far as the fix rate goes, as far as helping the programmers. So this was a rather amazing experience for me. So before I went into the company, I'd heard things like it's important to integrate with the workflows. I didn't, really understand that. I heard it, but I didn't understand it. And I didn't know anything about software engineering before coming into the company. But this is one of the cases where program analysis is learning from the programmers, not necessarily the other way around. Okay, so that's program analysis deployed in a way that takes seriously the hacker way, the iterative way of developing. And there's a few papers there, 2 papers there that relate this experience. Now I want to shift gears and talk a bit about analysis hacking. So hacking a program analyzer, not just hacking the way the analyzer is deployed to the people, but hacking the analysis itself. So the main point about hacking the analysis itself is we found ourselves not only deploying infer in a way that fit with the iterative way of developing software, we started developing our program analysis tool itself in the same way, in an iterative way. And what we would do is, instead of trying to make the tool perfect and then shipping it and then celebrating, what we would do is we would put out checks for certain bug types before they were perfect and iterate with the people. So then the developers would give us feedback on whether this check is good or bad, or the way in which it's good or bad. And then this would help us then tune the check and make it a lot better. And we found that the move fast and break things was like, the developers would rather us put out a check early and iterate with them to make it better, rather than wait, and only put it out at the end. Something more like the waterfall model of software engineering. Now, I'm going to now go into a personal example of this analysis hacking. So the context is, after being in Facebook for a couple of years, I had been a manager. I'd been the manager of the team, and the tool was starting to become somewhat successful. So I was getting itchy. I wanted to do technical work of my own. And my manager, Brian O'Sullivan, then shifted me over to a half-time engineering role, and then a full-time engineering role away from management. And I decided, what should I work on? I want to work on one of the hardest things I can think of, and that's concurrency analysis. And I had said this to Mike Hicks before that in an interview for his programming language enthusiast blog. I said, I want to understand concurrency scalably. I want to produce high quality reports useful to programmers. Then it could scale to many programs and many programmers. This seems pretty, when I said this, I mean, it was just an aspiration. But then when I decided to go into engineering myself, I said, okay, why don't I try that? I mean, that doesn't sound too easy, but why don't I try? And let me just remind you, the numbers at the bottom are just a reminder that if you try to look at all the interleavings in a concurrent program, it's not going to work very well. You very quickly run into the number of possibilities that are more than the assumed number of atoms in the universe and things like this. Enumerating the interleavings isn't a very effective approach. And that's one of the key reasons for why it's difficult. So at that time, I'll just put two bookends to the context for this. One of the most highly cited static analysis for concurrency papers ever, and a very, very, very good paper, was this Racer X by Engler and Ashcroft. Now this found 3 race bugs in Linux, 3 real race bugs in Linux that were fixed. That's not a lot of bugs, right? So when we're working on static analysis in industry, we're looking for impact. So usually, unless there are no bugs, usually we're looking for like hundreds, thousands, those kinds of numbers of bugs. But that was that bookend, and I really respect that paper. On the other hand, here's dynamic analysis. Many papers in dynamic analysis, they said static has proved to be difficult for concurrency, so therefore we're going to do a dynamic. One of the most successful dynamic papers is Thread Sanitizer by the folks from Google, and there are other ones that take that very same point. And the deployed things, as opposed to the things done worked on in the literature, tended to be dynamic, not static. And the reason was static is thought not easy. So I wasn't going to let that dissuade me. I had something in my back pocket called concurrent separation logic, which was a theory for reasoning about concurrency. And I thought I knew how to prove a lot of the programs. And I thought I could make an analyzer based on these ideas. And even if I failed, I reckon, well, why not? I think I'd like to have a go at this. So despite the fact that maybe static was thought not to be easy, I had my own way in, and I was pretty enthusiastic and stubborn. So, okay, so I wanted to make a concurrent separation logic program analyzer. And I wanted to be fast and compositional, but it's really a bad idea to just start from a very abstract point of view when your goal is to make a difference in impact in a reasonable amount of time. I thought, what I want to do is I want to understand the engineering context first. And that way, maybe I can prune what I need to do so that it's more realistic. So I spent these months, February to October of 2016, looking at vast amounts of Java concurrency code inside Facebook. I was doing mental program proofs in concurrent separation logic to see if I thought it would work and to see how I understood what was going on. And I started implementing a prototype concurrent separation logic prover. And in this time, there's nothing deep that you find out, but this is the kind of thing you need to do to scoping work in engineering. So I made 3 discoveries. One is that the Java code that was concurrent, it didn't have any thread spawning. It was all implicit, done in Android frameworks. And yet there was certain things that were supposed to be thread safe. So this saved me a lot of time. I didn't have to deal with explicit thread spawning in my analyzer. I had wasted 2 weeks making an analysis algorithm to deal with thread spawning, but then I realized I didn't need it. Instead, I would try to make sure that the thread in a thread safe class, that the different methods didn't interfere with one another, was what I would try to do instead. That was interesting. That simplifies the problem. The discovery number 2 was that all of the code I saw, or maybe 98% of it, I could prove, or so I thought, when it was correct with concurrent separation logic and fractional permissions. So here's an example. So the developers don't just lock everything, right? Because that's too expensive. So here's an example. There's a comment from some Facebook code, but it's open source Facebook code. And it's saying, this is written to only by the main thread with the lock held, read from the main thread with no lock held, or read from any other thread with the lock held. So here's a small program showing this. So we write to X inside the synchronized block in the first thread. Then we read from it outside of any synchronization. In the second thread, we read from X inside synchronization. Now this is okay. This is race-free because the write in the first thread and the read in the second thread are synchronized, so they can't happen at the same time. Although the read in the first thread is not synchronized, it's okay if it goes at the same time as the synchronized in the second thread. So it's okay. And so we won't look at this little proof in detail, but I was able to do little proofs like this in concurrent separation logic with fractional permissions. And it was all working out very well. It can explain these kinds of idioms very well. The third discovery was that synchronized this was by far the most common idiom. So sometimes you had 2 locks in a file. Very, very, very seldom did you have 2 locks in a file. Usually it was just synchronize this. So my plan was I developed an algorithm to infer what's called resource invariance and preconditions, an abstract interpretation algorithm, which I thought would cover 98% of the code that I had seen. It ignored multiple locks to get started, and I just began implementing. And I had a grand plan. I was very excited about this grand plan. So my plan was, I'm going to ship this analyzer in about 1 year. And I think it's going to find hundreds of bugs. Remember the Ashcroft Angler paper, which I greatly respect, found 3 bugs. I thought, I'm going to find hundreds of bugs, was my grand plan, and I'm going to prove data race freedom for thousands of classes and hundreds of thousands of lines of code. I was extremely excited by this. I thought that would be a lot of impact. And furthermore, it will be done with a beautiful proofer. And so I liked this idea. But after 10 months of work, I had no impact at all. But the Facebook management saw this plan unfolding, and they thought, this sounds good. If it works, it'll be great. If it doesn't work, we'll learn something, was the kind of thing that was being said to me. So that was great. Then something happened. So sounded like a good plan. But then my colleague Sam Blackshear on the Infer team, he was making periodic updates to all of the Android programmers at Facebook saying, this is what we're doing. Now, in one of his updates on October 14th, 2016, he said, there's also a fancier concurrency analysis in the works for checking that thread-safe annotated classes are actually thread-safe. And this is referring to the work I was doing. He did this without me knowing. I mean, Sam just said this, and so he did it. And then the first comment back from the Android programmers was, will the eventual thread-safe annotation be recursive? So first of all, they didn't respond to all the rest of the update. They immediately responded to this. Then they said, will it be recursive? Recursive was their way of saying interprocedural. The first thing they asked for was an interprocedural concurrency analysis. And here's the reason, because they were about to embark on a project to take Facebook's Android app and convert it to a multi-threaded context from a single-threaded context. And multi-threaded UI is arranged in trees, and the nodes of the trees are classes or they're objects. And so it turns out that the mutation happens in the leaves of the trees. And so all of the races that would happen would be interprocedural. None would be intra-procedural. So an interprocedural analysis wouldn't have been good for this. So they knew this, although they used the word recursive. They asked for that right away. I thought that was quite interesting. But anyhow, I had my plan. I was going to release this prover in about a year. They wanted this now. They had this important project, but I had to do it in a year. Okay, I kept my head down and I just kept working towards my plan. But then I started to get further messages. Here's one of the messages from a manager, Jason, in New York. He says, "Hey, Peter, I usually work in New York, but I'm coming to London. I'd love to talk about what we're doing and how it could dramatically help us in H1. That's half one. And so here I've got a team saying, we really want you to help us. Now, that's not, you don't always get that in static analysis. In static analysis, you can get, we would rather you didn't bother us, is something sometimes you would get, or please don't cause noise or slow us down. But here we've got a team saying, you can dramatically help us. And yet I had my plan, which would take me a year out. Now, I had two choices. I could say, sorry, I'm going to keep to my plan and I'm going to ship my analyzer in 1 year. Or I could say, I'm going to change my plans so that I can help these people. That's the right thing to do in industry, or most of the time, is to say that I'm going to change my plans and help these people. And that's what I did. I knew that to change the plans to help the people, I knew that what I couldn't do is complete my beautiful prover within a year and have a low false positive rate. So I was going to need to compromise. So I did. And so what we did is me and then Sam Blackshear sat down with the Android engineers, Benjamin Yeager and Jingbao Yang in New York, and we together spec'd out a minimum viable product that would help them. So it's not that I dreamed what they wanted and then I gave it to them. We spec'd it out together. Let's say that two of the main things is when I said I can't give you the prover in 2 months, they said, find most of the races, high signal, but no need to provably find them all. In the end, the developer is going to make the call as to whether the code goes into production, and the analyzer is there to help the developer, not to block them. Another interesting thing is point number 5. Don't bother with fine-grained locking. So the first thing a scientist wants to do is to go for intricate, tricky examples, right? Like non-blocking concurrency, things like this. We would like to go for that. Hand-over-hand locking. We would like to do that. It's fun. They said, don't do that. The vast majority of the code is coarse-grained locking. And as the example I showed you earlier, there are some subtleties, but the product programmers are going to be involved in coarse-grained locking, and we want to help them not get into situation with data races. Now, the minority of the code, the framework code, would involve the fine-grained locking, and that's looked after by the real concurrency experts. So help all of the people before you help all of the people before necessarily you help these experts in what they're already good at. So this was really great. This constrained what we did. So we wrote a paper and we made an analyzer, and the analyzer has some abstract domains, and it's a compositional abstract interpreter. Now what I want to do is a demo, and I'm a bit worried that the screen isn't going to share properly now. So Christoph, can you tell me?
Yes, I'll stay on top of what's happening. And
are we seeing some code now?
No, we are still seeing your slide.
Ah.
I think it's sharing the window that you have there. So
are we seeing it now? Are we seeing some code now?
No, I believe you have to unshare and then share a different window.
I see. So I'll stop the share. Then I'll try to work out how to do this. Screen share.
Certainly a new set of challenges for all of us.
Yes. There we go. Share.
Yes, that looks like
yes. Oh, this is new for me too. I've never given a talk on Zoom before. So this was like the example from earlier, right? Race with main thread.java. So here we have a protected write on the main thread is we see synchronized this and mcount gets 1. An unprotected read on the main thread. So we've got an assert which says we're on the main thread. So these two, the first two, they can't interfere with one another because they're on the same thread. We have a synchronized protected read off the main thread. Oh, that's all okay. But then we have a protected write off the main thread. That protected write, that can interfere with the unprotected read on the main thread, right? That can interfere. And so now if I was to run infer, then it finds that, and there's a report. And if I'm to, probably if I do this, if I that's not the right way to do that. If I was to comment out that protected write off the main thread, then hopefully, if there's no syntax error, now it's not going to find the database.
We can't see the infer window because that's a separate window.
Oh.
I assume at least that you have an infer window open there.
I do. Okay, just don't worry about it. So
yeah, but we believe you.
That's okay. I'm still going to do this because I'm really determined to get part of this. There, so no issues found. And then you see what it does in for report. It creates a summary for each method. And so the summaries it records things like accesses, that there's a read of m count, and there's no lock held there, or that there's a write of m count and there is a lock held. It records information like that. So it records information about accesses and information about ownership. It's just a completely compositional program analysis. And I was going to do more with this this demo, but yeah, the switching between screens and stuff like that on Zoom at the moment is not working too well. So I'm just going to go back to the talk. Now, okay, what are we seeing now?
Currently, we see your file browser applications.
Do you see? You don't see the talk?
No.
Okay, sorry about this again, people. So share. How about that? Now we see the talk.
Yes,
again, right?
We see the talk again.
Okay. So there's a compositional program analysis that keeps track of information about what the current thread is, information about ownership, information about accesses, and what it does is it does that for each procedure. It does it without examining the entire surrounding context like a compositional program analysis does. And that's what allows it to go fast. So, okay, so we won't do the remainder of that demo. Now, the impact of this, was quite good. So, you recall earlier, what I was hoping to do was to find hundreds of data race bugs and prove thousands of classes data race free. Well, I didn't prove any classes data race free, but in 1 year in production, it found over 2,500 data race bugs. And there was no false negatives observed in production from this for over a year. Although I can trick the analysis, there was none observed in production. So this just illustrates the kind of impact that you can get by working together with the people, with the programmers, to give them what they need, as opposed to dreaming up what they should have beforehand. It's very powerful when you do this sort of thing. And then besides the numbers, some of the important engineer comments were like this. 3 thread safety violations are useful because they help us catch nasty and hard to debug bugs. This allowed us to ship newsfeed layout on a background thread and get huge wins in terms of scroll performance. So huge wins in terms of scroll performance, that can impact engagement and other even bottom line company metrics. So metrics that are described not in terms of the static analysis. And then the final quote is one of the engineers said they couldn't have done the multi-threading without this program analysis sitting beside them. So that worked out quite well. I was very pleased with that from it as an engineer. As a scientist, I wasn't too pleased. I wasn't too pleased with this as a scientist. I compromised, right? And it let false negatives in the door. Oh, oops, false negatives, oh no. We had let those in. And so we started to take some steps to try to limit the false negatives so we could prove a quotes soundness theorem. So Nikos, one of the people on the team, he implemented an alias analysis to try to find more bugs. Result, blizzard of false positives, couldn't put it into production. Sam, so he did an escape analysis to try to find more false negatives. Note, these weren't false negatives we had seen in production. These were just ones we knew we could trick the program analysis with. Too many false positives, blizzards, couldn't put it into production. My favorite was complete the beautiful CSL prover, compute separation logic prover, and then do a switchover, but I couldn't do it because the gap between the prover and the in-prod analyzer was growing instead of shrinking. Couldn't do that. Then one day I said, stop this. Instead of trying to change the analyzer to fit the soundness theorem, we know that this analyzer is working well. So let's try a different theorem. And so that's when we came up with this thing, the true positives theorem, which is that the analyzer reports no false positives under certain assumptions. And the assumptions had to do with what we observed in the product code, not the infrastructure code at Facebook. And the theorem wasn't true of the analyzer when we stated it. It still isn't quite true, but it helped guide the design of the analyzer. So we made changes, like there's something called the deep ownership assumption, which is if you own x.f, then you also own x.f.g. This is consistent with the true positives theorem and inconsistent, or it's not what you want for soundness in the sense of overapproximation. And so we used this theorem as a guide to help us change our analyzer to make it more under-approximate over time. So that's an interesting thing, to develop the theory to help the analyzer as it's in flight, not just to bless it afterwards. Okay, so now we get to the next part. Now, this is going to be difficult. This is not difficult because of the theory. It's difficult because of my use of Zoom. So this is related to a paper I wrote in Popl called Incorrectness Logic. And there's a talk on YouTube about this. I'm not going to repeat that. I'm going to say some of the same ideas, but now from a more program analysis slant to do with the audience that we've got here. Now, what I would like to do is run this, but I don't think it's going to work. And in fact, it's not going to work because I have some animation on this slide. And so, Christoph, I'm going to press play. You're probably telling me that this is not working, right?
I see no animation. I'm sorry.
Okay, we're not going to do that. So I think maybe I'll learn to use Zoom a bit better before next time. Now, what we can do instead is we can go forward to and we can talk about the main concepts in more mathematical notion. So,
Peter, there is an idea that I have. If you want to go back to the animation slide, try unsharing and reshare again. And this time when you share your screen, select the little button on the bottom, just before you confirm sharing, select the little button that says that you want to share a video. So a little checkbox.
Optimize screen share for video clip?
Yes, try that one.
Oh, that could be awesome. That could have saved me a lot of problems.
Sorry for not thinking of that earlier.
This. Is that working?
I'm afraid I still don't see
animation.
No animation. I'm sorry.
No.
Sadly, no.
Hello?
Hello, we can still see you, but you're not sharing right now.
Have I got you back?
Yes, we can see the slides again now.
Right. Christoph, do you hear me?
Yes, I can hear you. Can you hear me? Just checking. Is my audio off?
So, Hello.
Can you hear me?
I don't hear you.
Um,
Can you hear me? Christoph, can you hear me?
I can hear you. I think that Peter can't hear us at the
I don't
moment.
hear you, Christoph. Do you hear me? Nod yes if you do. Okay. How about if I share my screen and just go back to it?
Yeah, the slide.
Okay, we're back. Christoph, nod if you hear me. Okay, so we're not going to do it. We're not going to try the animation, even though the animation is quite nice. Okay, so what we've got is we've got these triples. So the Hoare triple can be defined as the over approximate triple at the bottom. That says that X, R, Y, if R as a relation holds, if Y is a superset of the states reachable from X by the program R. The under approximate triple X, R, Y holds if if Y is a subset of those. So that's what the incorrectness logic is based on. It's based on that idea. Now, what we can do, which is quite interesting. Oh, this is really going to have a hard time working. Oh no, it's not going to have a hard time working. What we can do is, for instance, let's look at this loop. So the Kleene star, what we do is we execute X gets X plus 1 over and over again, and then we exit the loop. Now, client, we get a bug because we can reach a state where X equals 2 million. Now, you could find this with bounded model checking by unrolling the loop 2 million times, right? But there's a different way to find it by observing that X is bigger than 0 is a true under approximate assertion after the end of the loop. Now, if we observe that X is bigger than 0 is a true under approximate assertion, it means every state satisfying X is bigger than 0 can be reached from this program and from loop 1, and it can. And once we know that, then we can prove that this loop is reachable, and we can prove it without examining all of the unrolling. So we can do it very succinctly. That's very interesting. How are we going to do that? We're going to do that with an interesting proof rule, which isn't like Hoare's proof rule for while loops for over approximate logic. It observes that for under approximate reasoning, there's something like a liveness property in play. So from every state in the conclusion, you can get back to the presumption by running the program backwards to at least one state in the presumption. That's sort of like a liveness property. And we have a proof rule that's sort of like normally liveness proof rules decrease something going forward. Here we decrease something, the P of n plus 1 going backward. And we get this proof rule for reasoning about loops, under approximate loops. And with this proof rule, that's how we can prove the under approximate conclusion, X is bigger than 0. Like there's the instance around lines 20 and 21. It's gotten by choosing my P of n is X equals n. And it uses the backwards variant proof rule. And so we can prove that we get the bug much more succinctly than we would have otherwise done. And we get a much more general summary, so to speak, for loop 1. Well, that's very interesting. So what's very interesting is it opens up some possibilities for program analysis, but also it does that, but it's also highlighting we're using a different kind of proof rule than the one normal from Hoare logic. So you might think if you look at the over approximate triple and the under approximate triple that, well, they're just dual. Well, the definitions are dual, but sort of the reasoning you do with them isn't dual. I want to like explain that a bit more now. I explain it as follows. So here are some proof rules for iteration. So the top left rule is Hoare's proof rule for loops. The top right rule is a true proof rule, but it's usually omitted from Hoare logic. It's usually omitted. We'll come back to why that is in a second. That's very interesting. The bottom left rule is a true rule for under approximate reasoning, but it's pretty useless because you stay inside the initial states. The bottom right rule is the rule that I've just talked about, in slightly different notation. And you can't omit that from incorrectness logic, where you can omit the top one from Hoare logic. This is getting at why they're not dual, and this is really quite interesting. Now, the reasons for why that can be summarized as follows. For over-approximate reasoning in Hoare logic, we say that a superset of the reachable states is an invariant. A subset is inductive if it's closed under the transition relation. There's a classic result, completeness of inductive invariance. Any invariant is the superset of some inductive invariant. That's why you can omit that previous rule from Hoare logic, because if the human guesses the invariant on the left, then you can just use that proof rule. And completeness of inductive invariance means you don't need the right proof rule. On the other hand, for incorrectness reasoning, there's nothing that's playing the role of inductive invariance in Hoare logic. Okay, that's my. That was my alarm. We've gone a bit over. Okay, so there's nothing playing that role, and you can see that this incompleteness is true, and that's another way of explaining that they're not just quite dual. Now, I'm going to do another thing. Now, the last bit I'm going to do, technically, is I'm going to take a step towards abstract interpretation, but I'm not going to quite go there. I want to show you what's happening in the under-approximate or incorrectness reasoning from a lattice theoretic point of view. So this is where, if you're not all familiar with lattices, just relax for a minute. But if you are familiar, then this helps to clarify. So there's the correctness problem. So F is the transfer functions. Least fixed point of F is like the global semantics of the program. S is a specification. What abstract interpretation does is it tries to find O, which over approximates the least fixed point. That's what it does in order to show correctness. What I've been talking about, the under approximation can be described lattice theoretically as, say, find U, which is an under approximation of the least fixed point. That's where U is not does not satisfy the specification S. It's not dual because the dual of correctness, it seeks an under approximation, but an under approximation of the greatest fixed point rather than the least fixed point. So there's correctness and there's dual correctness, which I've taken from this paper of Patrick Cousseau on the bottom. And this incorrectness stuff, it's a bit different because it's this thing in the middle. It's this thing in the middle, and you're trying to under approximate the least fixed point, which is why all of the standard theory doesn't just apply immediately by flipping a lattice upside down. Now, so we're here. Now, there's something very interesting now. If we look at, I'm probably going to go like 3 or 4 minutes late here, but if we look at the two proof rules I talked about before, that's a sound proof rule of Hoare logic on the top. That's a sound proof rule of incorrectness logic on the bottom. What they're trying to do, the proof rule on the top, is if you get the Kleene sequence for fixed point iterates, each of the PI or P of n's, it's trying to get above the corresponding element in the Kleene sequence. And that's why that proof rule is valid. The one at the bottom, each of those things is trying to get below the corresponding thing in the Kleene iterates. And that's why that proof rule at the bottom is sound for incorrectness reasoning or for under approximate reasoning. So that's very interesting. Oh, geez. If only I could bring that one in, but I can't. So, no, I'm not going to be able to do this. Okay, so what I was going to say here, but it's not going to work because I can't do the animation, is that similar thing is happening with widening in abstract interpretation. What widening does is it uses a binary operation which over approximates disjunction in order to try to get above the Kleene iterates. In under approximate reasoning, there's a corresponding notion which we call submersion, which is an under approximation of disjunction, which tries to get below the Kleene iterates. And so the dual concept would be an under approximation of conjunction. But the non-dual, the thing that's appropriate for incorrectness reasoning, is to be an under approximation of disjunction, which again lets us get below the cleaning iterates. So this submersion, which I wasn't able to show the exact definition of, it's implemented in this infer.pulse, the pulse analyzer of Jules Villard at Facebook. And all it does is it drops disjuncts, and it's a similar concept to widening, except appropriate to under approximate reasoning. Okay, so to summarize, so thank you all for listening and for putting up with a few of the hiccups with me dealing with Zoom. The one thing I want to say, I think in conclusion, is that I started this work as a theorist. Then I went to Facebook and I learned a tremendous amount from the programmers, from the software engineers, an amazing amount. This helped us make better program analyses. Then, oh my God, we made new theory too, because it made us bump into problems that we hadn't bumped into before. Now we're going back and making better program analyzers. So the state of program analysis when you work in industry is at this interesting point where you can have the practice and you can have the theory playing off one another in a really tight iteration loop. And this leads to good results, but it's also very interesting, even scientifically, because it leads to the new theory. It's interesting from engineering because it leads sometimes to better practical results. So it's a very healthy place to be at the moment, is working on program analysis in industry. Okay, that's a good place to finish. Thank you.
Thank you very much, Peter.
Thank you.
So this was a very inspiring talk, and I'm very sorry for all the technical issues that we have to go through. Your talk was the very first talk that we have in this format, so that is the, in a way, I guess a big part of the reason for why we don't know exactly everything quite yet to make Keynote and other tools work. But now we have some 5 or 6 minutes for 7 minutes even for questions. Now nobody has asked any questions on the thread for your talk yet, so I am not sure if that means that there are no questions.
Well, I could ask Peter a question while others type their questions.
Yes.
So, very interesting talk, Peter. You talked about hacking analyses. So in your experience, when you start hacking analyses, is it that it should have low false positive rate at the cost of high false negatives, and you keep improving that? Or is there
I'm not hearing Patty. I'm not hearing Christoph.
So I think I know how to fix that.
Maybe I can type the question.
Can you stop screen sharing, please, Peter?
No, I think screen sharing is stopped by Peter.
It did.
It stopped? Okay.
So, you can't still hear me, Peter? No.
I'm not screen sharing anymore.
Yeah, I'll probably type this in. Oh, there's a... Peter, can you check the Slack channel, or you're not on Slack? Because there's a question from Alistair.
I will temporarily suspend Peter and re-promote him. 1 second. I'm not seeing a reaction here, interestingly. Okay. Okay, we have some first questions, some first other questions now, but there we go. I'm re-promoting.
Peter there, he seems to have dropped out. There is.
Yes, I demoted and repromoted him. That should have hopefully reset his setup.
You may have to unmute him so that
he's unmuted in my setup. So I don't fully.
Okay.
Are you back, Peter? Can you hear us?
We could hear him, but I don't think he can hear us.
I'm not muted anyhow.
We can hear you, but I don't think.
Okay, Christoph.
I
can't start the video.
So Peter's in some sort of weird state in my Zoom.
Can't hear you either.
I can't do anything with change any permissions for him. I can't click on him. So
can you hear me?
Yes, we can hear you.
Do you want to post a question for me? Do you want to type a question for me?
Yes, let's just do that. Let's ask the questions in text chat in private text chat to Peter, and then he can answer to them. So I will start with the ones in the chat. We have one from Alistair Donaldson who is asking. He says, "Thanks for the talk. Getting a soundness theorem that suits the code base under analysis is interesting. Do you think that working towards that theorem changed the usability usability of the tool for the developer?"
Yes, so getting a soundness theorem that suits the code base under analysis is interesting. Do you think that working towards that theorem changed the usability of the tool for the developer? Yes, I do, because what it led to is fewer false positives. And then this was a win for the it helped in two ways. First, it helped have fewer false positives, and second, it helped simplify the tools so we could iterate quicker and help the developers more quickly. So the answer is yes, but going for the wrong soundness theorem would harm the developers. From Julio Lual, is there a risk that they'll learn what the analysis do and still make bugs, but not the ones you can find? Yes, there's a very real risk of that. But although we didn't set out to get this, we found no false negatives from over a year in production. No false negatives were observed. So although that's an in principle possibility, and you can't predict beforehand what will happen, it worked remarkably better than I thought it would. So I feel like there might be some kind of completeness theorem hiding that I haven't done yet for this analysis, but it worked remarkably well in a way that surprises me and I can't completely explain, except empirically. No, so for the approach to happening analysis is the focus always on the small false positives and reduce false negatives? No, the first point of view is the first goal of the analysis is to help people. That is prior to concepts of false negatives and false positives and everything like that. So what I would do is I figure out, I want to help people before I think of those concepts. Then I can go in with the developer teams, and then I might fit some bits, some concepts from program analysis theory to what they want. But that comes second for me. So helping the people comes first, then we tailor what we want to do, maybe change what we want to do. So that's a really good question. So it's not necessarily that way. So there's another one. Could Peter share a bit more on the findings from the diff time results, and specifically what kind of project or issues are included that the statistics composing the 70% fixed rate? That was back in 2014, and it was our first analysis. It was looking for resource leaks and null pointer exceptions, and maybe a few other things on Java, in particular Android. The product was the Android app for Facebook, and including Messenger and some other properties, but it was including that kind of code. The code was big, and this has persisted over time. Not necessarily the number 70%, but how diff time gives us a much higher fixed rate than batch has persisted. And this has caused other teams in Facebook besides ours to try to change analyses to run them at diff time. So for instance, there's a team called Sapiens that has a dynamic analysis for Android, which is very clever analysis. They did an unusual thing to run that dynamic analysis at diff time because of this. So there is a movement, many people tried to run things at diff time, not just infer, as a result of this experience. Now, it remains that some things are too long running to run at diff time, like performance analysis. Often, there is some at diff time, but often performance analysis is too long running and it's run later. Fuzzing is usually run later, although again, there's a movement to try to do more fuzzing at diff time. Okay, I could go on and on, as you can imagine, but maybe that's a good summary response to that question. Building the MVP from ACE, how did you find out that the usage of threads was not explicit? Did you mine this? Or did you find out by talking to developers? Here's how I did it. I used grep first, and I didn't find any of the Java correspondings of spawn. Then I talked to the experts, and actually the experts I can't remember which experts I talked to. Then I talked to them and they said, ha, of course you don't need spawn. I can't remember the Java notation for spawn, but that's what happened. Is the analysis of infer incremental? Yes, that it's incremental. That's the most important thing about it, why it can run at diff time fast. And that stems from compositionality. So the compositionality was already there in our Popolo 9 paper, but we didn't know how powerful it was. So the incremental aspect is the number one, besides precision, is the number one most important thing that lets us work fast with the programmers. Do you think that running analysis in the IDE could have even more context than, I don't know about more context. See, IDE has to run even faster. Diff time, we need 15, 20 minutes. IDE, we need seconds. It turns out that RacerD, apart from parsing the code and everything else, is fast enough to run in the IDE, but not all of the infer analyses are. There are efforts to put more stuff into IDE, and it's just a lot of engineering work. So it's on our radar. Well, the question is where it comes on the priority list, but yes, it makes sense that the more you push to earlier in the process, the better. So IDE could be a wonderful thing, and there's the tech to do it. So this is the thing in program analysis. There's a lot of things we sort of know how to do, but we haven't explored it all, not just my team, the whole subject. There's loads and loads to explore, and that's a good question and a good suggestion. From Paul Gazzillo, Central Florida, challenges in generating bug course. Yeah, easy ways for the developers to understand. It's totally true. And this is where iterating helps, because we gave some reports to developers and they would say, oh, we don't really understand that. Can you change the way the report is? And then we would iterate with them to try to find, say for concurrency, what the good reports were. There was even an entertaining case in concurrency where we found too many similar bugs. We spammed the developers once with 60 bug reports from one function. They were 60 distinct races, but then the developer said, listen, this is just too much information. Just give me 2 of the races and I can work out that it's problematic code. Oh, that's a good question from Sandia National Laboratory. So I think I can, let me say, watch this space for an under approximate version of some interesting concurrency logics. So the logics are being developed, and there's a paper called Incorrectness Separation Logic coming out in CAV, and have a look at that. In some ways, the incorrectness theory is more elegant than the over approximate theory for separation logic. And that's only a sequential paper, but there's very interesting things coming out there, and it's not all finished yet. But in some ways, I think it's going to be more beautiful than the original.
So the previous question was, what is being done to help the concurrency experts working on the framework code? Will you have returned to working on your beautiful concurrent separation logic analysis? Next question, Julia Belyakova, are there probably new applications at Facebook that do not satisfy the assumption of coarse-grained locking or some other assumptions made in the tools? What is your next challenge?
Oh, yes. Oh, are there new, here, let me answer this. Are there applications at Facebook that do not satisfy coarse-grained locking? Yes, I've got one, but I'm not going to talk about it in detail. I've got some incredibly intricate non-blocking code that's very important. It's very important non-blocking code. And this is where we want to bring out something closer to full verification rather than automatic program analysis. And yes, in a company the size of Facebook with our tens and tens of millions of lines of code, you find almost all of the problems that you might want to find. And so I've actually got one of those that's occupying my attention right now. And it's very interesting.
Then we have one from Gabor Marton from Ericsson. Would it make sense to compare incorrectness logic to symbolic execution? As far as I understand, they both try to find one, hang on, where's my text? They both try to find one program point or path with a bug. I'll try to repost the question.
It would make sense to compare incorrectness logic to symbolic execution. So that's a good question. And in fact, my paper, it did this. I think it's correct to say the symbolic execution is a special case of the incorrectness logic. And I don't mean that people often say it's a special case so that the more general case is better. No, it is a special case, but the symbolic execution has achieved a lot. It's like very simple. It points out that there's a neat theory like horse theory that corresponds to it. And it also points out that there's a spectrum and there's other areas to play there. But it is already I've made that connection, and there's more to find out. I hope that so if you look at the original incorrectness logic paper, there's quite a lot of discussion at that point.
Thank you. Next one from Federico Poli at ETH Zurich. You mentioned that one of the goals is low friction analysis. In your experience, how much are developers interested in providing more annotations to get a better analysis?
Low friction. So the question is, how much developers are interested in providing more annotations to get a better analysis? It depends on the developer. It depends on the code base. And it depends on the problem that's being solved. So as long as the annotations aren't too bad, then they'll do it. For instance, null pointer annotations, they're doing it more and more in Java. As far as writing full functional correctness specifications for general code, I think the big problem is that they're hard to write. There's not many tools to help. And you'd like some payoff that's not only after the fact, far down the road. I think that there's a problem that we don't have, let's call it a pay-as-you-go model for writing expressive software specifications. We have a pay upfront model. Pay upfront, get payback a long time later. So just similar to the compositional and incremental way that static analysis can work that I talked about, I think program verification, if we could have more as a pay-as-you-go model, of how to apply it, and I think that feeds into some technical problems, then we would be in a better state. But it varies. Some people want to put the annotations in, some people don't. And from my point of view as an industrialist, I just have to respect that and try to understand what they need and provide help for them. It's a good question.
Thank you very much. Now for the last question, then we'll still have a bit of a break left from Marat Akin, JetBrains St. Petersburg and JetBrains Research and St. Petersburg Polytechnic University. Do you think there's a minimal amount of code/developer feedback needed to bootstrap the HackerWay approach to formal reasoning? If so, do you have any insight, or how could a regular academia achieve that requirement?
So I'm just repeating it so people hear on the YouTube channel. Do you think there's a minimum amount of code developer feedback you need to have to bootstrap the HackerWay approach to formal reasoning? If yes, do you have any insight on how regular academia might achieve that minimal requirement? That's right. One thing that I was thinking about when making this talk is, it can be irritating for an industrialist, especially a former academic, to say, this is the way you do it in industry, and we're making use of the developer feedback, and as if I'm lecturing you and saying you should do that, and I'm not doing that. I don't know the way you can get that impact, but what you can do is you can generate technical problems that are motivated by that experience. So for instance, the focus on compositional and incremental analysis, the way that feeds into the HackerWay, I would love to see more work on compositional and incremental analysis and more parts of the evaluation sections of papers focused on that instead of focused on the analog of the batch mode, which is how I see it now. The analyses of the scientific part of the paper, the tables, are all batch mode tables, is the way I would put it. So you can learn from that aspect, but I don't think it's fair to ask the academics to work with the developers in the same way the industrialists do. Rather, you can learn from some of the problems that we've encountered. So yeah, so that's a good, thanks for that question. It's important for me not to, give the impression that the academic researchers should behave the same way as the industrial ones, because we're all operating under different constraints. And so us industrialists really respect the scientific work that's been done, and we use it a lot. So.
Thank you very much again, Peter. I know that you can't hear me, but I've also sent you a text message. This inspiring talk, I hope, will give us all a bit of a bit of food for thought for how to proceed. For now, we have still a bit of time left. Some of you may already have left for the break. And for the others, now you have 5 minutes to get a coffee or something along those lines. And then rejoin us, please, at 20 past, whatever your hour is, to see our technical talks. First by...
Thanks, everybody.
Jishang Shen, and then by Michael Reif, by Xi Wu, then by Michael Reif, and finally by Raphael Mona. Thank you.
Hello, can you hear me?
Yes, works well.
Okay, that's good. Thank you.
Thank you.
Can you hear me as well?
Yes, I can hear you.
Okay, great. Thanks.
Hi, can you hear me?
Yes, we can hear you.
So both seems to work fine.
Yes, thank you. So welcome back, everyone. We are 1 minute late on account of a very short break. But next up, we have our 3 research talks for today. I'm going to present these talks as pre-recorded videos, and then there will be time again for questions and answers to the speakers. First up, we have Xi Wu from the University of Sydney with a joint work with the University of Athens on explaining bug provenance and trace weaknesses.
Hello, everyone. I am Xi Wu from the University of Sydney. Today, I'm going to present our paper explaining bug provenance with trace weaknesses. This is a joint work together with Zhixiang and Bernard from the University of Sydney, Neville and Yanis from the University of Athens. So, as we know, bug finding tools have matured, so they are widely used in the software development life cycle, both in academia as well as industry. These tools search for software bugs by checking programs' code using static program analysis techniques without executing the code. They not only improve the productivity of software engineers, but also lower the maintenance costs. Now, let's see a motivating example. This is a part of a Java program, which actually contains a non-pointer exception. If we look at this code in more details, we can see there are 2 classes, main and MPE, The NPE class only contains one method named return none. This method takes a string as a parameter. If this parameter equals to none, then the whole method returns none. The main class contains two methods, main method and also another private method named NPE call. This private method invokes both the return none method of NPE class and also the toString method. So if we put this example into a bug-finding tool, it may return you the following result, as I showed in my slides. It tells you that there might be a bug on line 11 in the main.java file, where I draw a red line in the example. At the first moment you got this information, as a software engineer, it may not be immediately intuitive to you to understand the true existence of this reported bug. So we have to look at this code again very carefully. I draw some arrows here so that we can easily find out that when the main method invokes the NPE call method, it passes none as the second parameter, which will continue passing to the method return none. So the variable result on line 11 equals to none. Then this none invokes toString, causes this non-point exception error. So here we find that if we can understand the connection between the root cause of a bug and the reported line number, then we can better understand the true existence of a reported bug easily. So the motivating example I used here actually is a very simple example which contains only a few lines of code. Now, let's assume we are dealing with a very complicated example, as I listed one on my slides. It makes the understanding of the reported bugs more complicated if we only know the file names as well as the line number of the reported, as reported here. So when we use the state-of-the-art bug-finding tools, we may have the following deep thinking questions. Why bugs were found? Could I also see the root cause together with the reported bug line number? Might I also have a comprehensive explanation for these existence reported bugs? Well, most of the art bug-finding tools do not explain why bugs were found, mainly due to coarse-grained abstraction, that they abstract away large portions of the operational semantics of the programming languages. Some bug-finding tools provide vague notions of provenance, such as reporting partial paths and heuristics to expose the root cause of the bugs, where most of the techniques are ad hoc, since the problem is really hard and undecidable if definite explanations are sought after. Well, in order to improve the utility of the bug-finding tools, our work devises a new technique, giving insight into finding the causal connection between the root cause of a bug and the reported line number to the end users. We will map an input language into a simple decidable machine called constant copy machine, the CCM, for provenance constructions. And also, we will use an abstracted flow-based semantics to overcome the problem undecidability and also to solve the bug provenance in polynomial time. Well, in order to achieve this goal, our work proposed a new computational model, constant copy machine, as I mentioned, which is also called CCM. And we also introduced the concept of trace witness to resemble the provenance of a reported bug. And then, based on the Florida-Walsall algorithm, we develop a new trace fitness generator and also evaluate our approach on some open source Java programs. First of all, let's have a quick look at our new computational model, constant copy machine. This is a simplified intra-procedure machine. Elementary instructions in a CCM abstract a behavior of a language with set effects, such as C, and also mimic the control flow of input programs via a control flow graph. The CCM is only for analysis purpose and not as an actual execution semantics. So a program in CCM is represented as a control flow graph. And here, V is the set of the program statements, and E is the set of control flow edges. R is the start node of the program, and F is the final node, which is usually an assertion. So I will introduce the assertion later on this page. A program path is a finite sequence of statements. Now, let's go back to the syntax of our CCM. Here we can see a statement in a control flow graph can either be a constant assignment or a copy assignment, or an assertion, as I mentioned just now, which is used to check whether the variable x has a certain value n in a node or not. And also, a statement can also be a no operation semantics. So after we have seen the CCM model, we would like to explain what does a trace fitness mean in our work. In fact, a trace fitness is a program path which starts from the start node with initial statement and terminates in the final node, which contains an assertion there. We provide a strong update semantics for our CCM, whose details can be found in our paper. I didn't list the very detailed semantics here in my slides. But here, I listed a semantics function, sigma, for program passes, whose intuitive meaning is that the evaluation of a program path P is the semantics evaluation of each statement on the path according to the context C. Now, we can see the trace witness problems in our work is in fact asks for a trace witness, particular a shortest path, a shortest one, for which the assertion A in the final node F holds under the program context C in the node. Besides that, we have also developed a new trace witness generator. And here I listed the overall framework for our trace witness generator. So in order to understand the trace witness problem on, for example, object-oriented languages, we use a translation approach, which we call it a gadget, to translate the input language or input program into our CCM. This gadget is composed of two parts. First is the dupe framework, and the second part is our own CCM gadget part, which means our CCM gadget will take the result from dupe framework for the input language. Then the main responsibility for our CCM gadget mainly focuses on converting programs with their inter-procedure calls into the intra-procedure cases. As we mentioned just now, that the CCM is a simplified intra-procedure machine only. Also, the gadget will map CCM trace witnesses back to the original input programs. So on this page, you can see the control flow graph in CCM for our motivating example, the NPE motivating example as I showed before. So here we can see two red boxes which are added into the control flow graph by our gadget, so that the inter-procedure calls in the input language can be converted into the intra-procedure calls, so that the whole language can be represented in CCM. Therefore, converting the input programs into CFG in CCM is the first step for our trace witness generator. Besides that, we also have another 2 steps for our trace witness generators. So the first one is what we call it the data dependency train computation. The third one is the shortest trace generation. So during the data dependency train computation, we would like to compute all the variables in the program which may contribute to the assertion, and also record the nodes which contains these variables. Then the shortest distance between every 2 data-dependent nodes in the data-dependent chain will be calculated based on the Floyd-Warshall algorithm, as I mentioned just now. As we know, Floyd-Warshall algorithm is a very efficient algorithm to find the shortest path among all pairs of nodes, which leverages the principle of dynamic programming to achieve its simplicity and efficiency. Even though it has the cubic time complexity, it allows the result to be queried multiple times without any recomputation, which may happen quite frequently during program analysis. So, based on the result we get from these 3 steps, we finally generate the trace witness that starts from the initial statement and terminates at the assertion node, which makes the assertion holds. Well, we finally apply our approach on 3 open source Java programs whose size can be found here through this table. The goal of our case study here is to find valid traces of NPEs reported by a Java non-point exception checker named Digger, which was developed by Programming Language Group in the University of Sydney. So from the result table here on the slides, we can see that around 80% NPE reported by Digger cannot find a trace witness, which illustrates that this NPE may be a false positive. But we cannot conclude that these bugs without the trace witness are definitely false positive. That is because some of these invalidations are caused by node unreachability. Besides that, our result also illustrates the efficiency of our algorithms, which solve the bug provenance for complicated programs in polynomial time. But except that, our result also brings us a deep thinking that maybe a better sorted path algorithm need to be studied so that our approach can reach a better performance. Finally, I would like to conclude our paper that in our work, we propose a trace witness-based bug provenance techniques, and we also introduce a new computational model, CCM, for the provenance construction. Besides that, we also develop a new trace generator based on the Floyd-Warshall algorithms. However, This is only the first step for our work. And in the future, we still need to enrich the CCM, for example, by adding computational statement. And as I mentioned just now, we would like to investigate other shortest path algorithms, for example, Dijkstra algorithms. The last but not the least is we would like to apply our approach to other kinds of exceptions. So that's all for my presentation. Thank you so much for listening.
Thank you very much. Now let me see. Yes, hello Xi, we have you on video now. So everyone,
Yes.
now is your chance to ask questions about Xi's talk. We have a good amount of time. We are doing very good on time overall, I would say. So please use the opportunity. So I'm not seeing any questions yet. So maybe one first
probably
question.
I first share my slides in case some audience would like to refer to my slides.
That's a very good idea, yes. Let's see, until we have questions, maybe I can ask one. So you've applied this now to null pointer exceptions.
Yes.
What do you expect different kinds of challenges with different kinds of bugs? Or do you have particular bugs in mind that whose challenges you thought about?
Okay, that's a very good question. So actually, as I mentioned just now, this project actually can be divided into several steps, and this work is really our first step. And in this work, we only focus on the NPE, but I think we also would like to extend our approach so that we can convert, so that we can be applied to other exceptions. And currently, we are still in the, so as I mentioned in my future work, we have several steps, and we are currently focusing more on enriching the CCM itself and also investigate for the other shortest path algorithms. So for the last point, I think it's still in our to-do list, but not a very, clear plan for the other kind of exceptions, but I'm pretty sure that our work can cover more types of exceptions.
Thank you. We have a first
you.
question from the forum, which is from Alan Cox, who asks, how does the translation to CCM work for interprocedural calls for example, recursive calls?
Okay. So currently in our CCM, it doesn't contain the recursive, but I mean, in my talk, I think especially for the gadget one that we currently focus more on the gadget to do the translation between the input language into the CCM. And I think that's really a good suggestion that we may consider the recursive later in the extensions of this work. But currently, this gadget will help us to translate the interprocedure into the intra one. And that is what we can cover currently.
Thank you. The next question comes from Paddy Krishna and Oracle Labs. Many data flow analyses keep track of trace. So is your technique specific to the use of data log?
No, not particular to the data. Yes and no. So yes, currently this work is based on the data log, but I think maybe it is not only specific to the data log. We can actually extend it to other ones, not only the data log.
So what specifically is it there that data log gives you that you would have to replicate elsewhere? Might be a follow-up.
Yeah, so, okay, I think it should go back to the gadget we used. So actually, as I mentioned, this gadget can be divided into two paths. The first path, actually, we need some help from the dupe framework. And as you know, dupe can help us to actually translate the input language into the facts, which can be directly used in the data log. So currently, because I think the dupe framework is very useful currently for our work. So that's the reason why we focus on the data log currently.
Thank you. Are there any further questions?
There's another question posted on a different thread, I see. On the thread advertising the question thread, there is a question. Does this need something?
That is not the thread for questions, but I will use this one once, and then maybe I should delete that thread to avoid confusion. Does this technique need some constraint solving to check the feasibility of witness traces? I have not seen some discussion of this from Ting Su.
Yes, actually, it needs to do some pre-processing, especially for the unfeasible conditions. Sorry, I'm not quite sure whether that is the. I might answer the question. I believe Ting asks that whether we need to do some pre-processing for the unfeasible nodes.
It was specifically for using constraint solving to check the feasibility of witness
the
traces.
constraint solving, yeah. Okay, sure. So it still goes back to our future work that, yes, I think we will use, currently we plan to use the solver like the Z3 for our future work so that we can cover more features in this framework. But maybe not particular to the constraint solving.
There are opportunities to ask follow-up questions, but I have one more question now from Mario Luca Bernardi. In the CCM translation, how do you deal with polymorphic calls?
Okay, so currently we didn't cover that part, unfortunately, yeah. But yes, so since I mentioned that we have the several steps and we plan to cover it in the extended work. So yeah, I believe, sure, because I mentioned again that this is the first step. And also the main goal for this first step is that we want to, by using CCM to weaken the semantics so that we can easily solve the problem in the polynomial time. So that is our main focus on this first step.
I see. Thank you very much. I think we're out of time for questions, but I very much appreciate your talk. Thank you so much again, and also for your answers to the questions. Now it is time for us to move on. And next up, we have a talk from Michael Reif, Florian Kübler, Dominik Helm, Bernd Herrmann, Michael Eichberg, and Mira Mezzini from TU Darmstadt. And I will let them speak for themselves.
Hello everyone, my name is Michael Reif from the Technical University of Darmstadt, and now I'll present our work about our new abstract interpretation-based intermediate representation. So, what is the problem we are trying to solve? We want to implement static analyses, and doing so directly on bytecode is quite troublesome. That is, because bytecode has a lot of different instructions actually doing a similar thing, and one also has to take care about Java bytecode's operand stack and its implicit control flow. That's also the reason why most static analysis frameworks with Java usually first transform Java bytecode in an intermediate representation before actually analyzing it. And the problem we have is that Opal still directly works on Java bytecode and so do all its static analyses, which makes it pretty hard to use, especially for beginners, because it requires a lot of knowledge about Java bytecode. To facilitate the development of static analyses, we want that Opal also benefits from having an intermediate representation, especially benefiting from a limited instruction set. For example, loading a constant integer in Java bytecode has 4 different instructions, whereas we could only use one for it, right? But intermediate representation also had other benefits, such as explicit control flow, that all the intermediate values have explicit names, and additionally also the nested control flow and the complex impressions are simplified. So most of the meter representations are based on a 3 address code, in short TAG, or additionally use the static single assignment form, in short SSA. Just to get us all on the same page, let's refresh what TAG and SSA actually is. First, to 3 address code. Here, every statement has at most 3 operands, 2 for the operators and 1 to store the result. It can also have less statements with less operators. Usually, all different statements types are still available, such as conditional and unconditional jumps, method calls and returns, and it can also have some custom instructions. To demonstrate its effect, let's consider the example in the bottom left corner. It shows a rather complex expression with 4 operands. When we transform this expression to TAG, it will be simplified into 2 different statements with 3 operators. SSA refers more to a property of a representation. As the name suggests, each variable is assigned exactly once. That means that it's always known where variable that it's used is defined. To keep that property when branches are present, SSA forms usually provide fee nodes to select the value from a certain branch. As we can see below, this property immediately facilitates optimizations. When we rewrite the code from the left to SSA form, we see that y1 is never used and therefore could be removed. And because we don't want to reinvent the wheel, we wanted to check what all the other frameworks like Zoot, Vala, or Hadoop are actually doing. All of them use intermediate representations, which are typed. Zoot, for example, uses Jimple, which is an optimized TAG representation that already applied some optimizations, for example, constant propagation. Hadoop, in contrast, uses Zoot's Jimple representation, which is basically Jimple transformed to SSA. And Vala has its own representation, which is also in an extended SSA form, and additionally captures local path conditions, which describe how to get in a branch. And all those representations are differently typed to a different precision. So when we consider the following example on the left-hand side of the slide, we see in line 1 that there's a collection, and then, depending on some condition, in one branch, the collection is either instantiated to an array list or to a vector. And then in line 7, we have a call on that collection and add null. What Vala's IR is capturing here is only the declared type of a collection. So in line 7, when we would consider a class hierarchy analysis call graph, Vala would consider all subtypes of collection as viable targets. Zoot does a bit more of optimizations here, as it computes the upper type bound of C from both branches, which basically looks for a common supertype of array list and vector, which in that case is list. So in a class array case, only all subtypes of list would be considered there. But optimally, we would like to have the information available that C can either be an array list or a vector, because that's the only types that are assigned to C. With that in mind, we finally come to our approach. Since I already said in the beginning that we use Opal, Opal's unique feature is that it does interprocedural abstract interpretations of a method's bytecode, and when we could use the information gained from the AI, that would allow us to build different immediate representations at different precision levels. Because when we exchange and customize the underlying abstract domains that are used by AI, then we can also adapt the outcoming immediate presentations, because we probably have more information. Opal usually already computes the method's control flow graph and also the views and use def information during AI and use it there. So when we have more abstract domains and detect that path and so on, then it would also result in simpler and less AR code. Opal's abstract interpretation is easily configured via Scala's mix and composition. So the semantics for each set of closely related instructions and bytecode is implemented in a single trait. So for example, there's a trait for integer-based operations where you can specify how certain integer instructions should be interpreted. And there are also domains for reference value-based operations and so on. For example, like instance objects, casts, tests against null, and other things. And those different traits can be stacked, and they can also interact together over a shared set of query methods. For example, when you have a trait that handles reference values, they have to implement the method is null, and then this is, for example, required for method invocations, because when you know that a value can be null or can't be null, then you either don't have to or you explicitly have to trigger a null pointer exception in Java. But I don't want to go into too much detail here, so when you want to know how Opal's AI works, you can follow the link or look into the SOAP paper from 2014 and get more details there. All you have to know here is basically that Takai uses pre-configured domains from Opal, which are just named like level 0, level 1, and level 2. Our intermediate representation called Takai has several features. At first, and it's an IR, which is in-straight dress code, and it is also an SSL-like form. It's only SSL-like, I will come to that in a second. As I just said, you can configure it by using different abstract domains which influence the AI construction. Currently, we have 3 representations available. From the 3 abstract domains that are pre-configured in Opal, we have a Takai L0, L1, and L2. And those explicitly encode the views information and use def information. They are just available in the IR and you can access them. It's only SSL-like because Takai doesn't support v-nodes. Instead, it uses union and intersection types for referent types values, and for primitives values they are captured via abstract sets, ranges, or values. But that the actual representation depends on the AI abstract interpretation domain that are used and how the values are abstractly interpreted. And the AI allows you to also encode additional information, for example, if a variable is null or not. So before we jump into how Takai actually looks, we want to consider the following source code example. At the first 2 lines, there are just 2 method definitions. They're pretty simple. One just throws the runtime exceptions and the other one just prints a string. And then there's the method we will see Takai in the next slides for. There's a method m, which has 1 parameter here. It is serializable, called serializable. In the first line of a method, we check if the given parameter is null, and if it's null, we return. We already gained some information here. Then we have an object O, a local variable O, which casts is serializable to a clonable, and then we also call the object's toString method, save the string s, and then we create 1 new string buffer, sb0, and append s using the sb0's append method, and get another string buffer. For all of those that don't know the string buffer interface, the string buffer usually returns a self-reference. And then we have an if check if those are basically the same reference or not. And if not, we throw a runtime exception. That should basically never be the case, right? But we can't know from that code or from the bytecode. And then we call the p method to print a string, and we print a string that from the actual string buffer. Okay. How does the tag from this look like? So the baseline tag, which is the least precise tag representation, is roughly as precise as simple, and this does not provide much more information than the original bytecode. But on the left side we see how it looks like. We still have the if statement, and if it's p1, so p1 is the parameter we get here, is not null, then we jump to the next statement, otherwise we return. Then we have the cast to clonable, and afterwards we have the information that p1 is the subtype of clonable. Then we continue basically like the bytecode. It's nothing interesting. It basically resembles what we just saw in source code. One interesting thing here is that what I just said is that Takai also catches the views chains immediately. So what you see at the sample at the right hand side is basically immediately available in Tag. It says for the parameters the use sites at A and 11. P0 resembles this parameter of the method, and P1 resembles the parameter that is passed to the method. which basically says the origin. When we use the domain L1 to generate a tag, we have already a bit more information, and all the changes are marked in blue color. Takai L1 already computes union and intersection types, and we can see that at line 2. Previously, from tag L0, we knew that P1 is a subtype of clonable, but now we know because it originally was a serializable, so the parameter 1 has to be serializable, and then it was casted to clonable. We know that's an intersection type from serializable with clonable. And we also know that P1 is not null because of the null check from line 0. Other things that Takai L1 already provides are must alias information for reference types, and it also applies constant folding and propagation to integer values, which can't be seen here. And also it prunes that paths if it's possible. So when we know that a condition is always true or false, then and that's why the rest of it is removed, because it has no use. Please note that at line 7 we now introduce a no-op. That's because the CFG is usually not rewritten and the basic block can't be empty, so that's why we have to add a no-op here. And now the if check and the call to the method that throws the runtime exception could be removed, because we know that the variable is never used and the expression value is ignored. And that's possible because tag L2 does selective method inlining, which is particularly useful for fluent interfaces, such as the string builder string buffer is 1 with append. Fluent interfaces have the property that they're usually allowed to chain method calls and then return a self-reference. So that's basically all the properties of Takai and how it looks like. And next we can jump into our evaluation. To evaluate it, we had seveal research questions. At first we wanted to know whether the performance of Takai is still reasonable, because we have to perform abstract interpretations and we wanted to know if it's fast enough and feasible. Then we ask ourselves how the improvement in domains and using more precise domains influences the number of discrete dress code statements in general. Then we also wanted to know how many times we have more precise receiver type information compared to simple. And we also wanted to know how using Takai affects the precision of subsequent analyses, in particular car graph algorithms, which we tested here using a simple CHA algorithm, because you can see the effect there immediately. So the first experiment, we wanted to know Takai's performance implications. And when we consider the table on the left-hand side and there the runtime column for our 5 evaluation projects, we can see that simple is almost, for the projects, slower than even the most precise Takai version with the level 2 domain. It's only slower for JavaCC. Then we can also see that the overhead from computing Takai L1 is almost negligible over computing Takai L0. So we conclude that it's in general feasible to use Takai, because it seems to be at least fast. But what's about the number of instructions and serial dress code statements? Now we know that it's quite fast, but as we can see, when we use a more precise domain, the instruction count is barely reduced for all the projects. So it's actually always less than 1% reduction in instruction counts. However, that's kind of expected, because otherwise it would indicate that there's a lot of that code within the project, and the interpretation finds paths to prune because they are never used. So it's actually good for the projects that we couldn't reduce the instruction count that much. But please be aware that all the projects are rather small, and bigger projects might yield other results. Next, our third research questions about the precision of Takai's receiver type information compared to simple. What we did here is we looked for all invocation statements in the projects and tried to compare the results, the types, with those provided by simple. As you can see here in the table, there are many invocations and we could almost match all of them. The most failed ones in ProGuard are due to a bug in Shimple where it falsely eliminated JVM level exception handlers, which are obviously couldn't be eliminated. So there were some call size that we couldn't match, but all the others we could match. And we found that the type information for most of them are equal. So Takai couldn't be more precise than Shimple there. But as we can see, Takai was always at least as precise as Shimple, but in some cases was also better. So we have a little improvement. And additionally, which is not available in Shimple, but we immediately have available in Takai, is nullness information, which we compute at more precise domains. So they are not computed with the base version of Takai. And here we see that we can provide nullness informations for a lot of core sites, and there we don't have to consider null pointer exceptions. In our last experiment, experiment 3, we constructed a simple class hierarchy-based call graph, and we wanted to figure out how Takai improves over Shimple. And in general, we see that we have a great reduction in call graph edges compared to Shimple, even though we couldn't improve that many call sites. But when we could, we had obviously way more precise information. The biggest difference is for JAX, which is almost 60%. But between the different versions of Takai itself, from level 0 to 2, we have a really minuscule reduction in call edges. So, to conclude, and to show you some future work, what we did in this work is that we extended Opal with Takai. It facilitates static analysis, and we don't have to implement them longer on Java bytecode. Then we also have an intermediate representation that's configurable over abstract domains. We provide 3 preconfigured domains that are really available as Takai L0 to L2, and we figured out that Takai seems to be feasible. But our experiment shows that we still have to experiment with different domains and trade-offs. Also have to do more experiments. And we also want to check out whether we can encode other information within Takai, e.g. string tracking information, by using abstract interpretations over strings in source code. Finally, let me summarize what we talked about. So at first, we figured out that what other intermediate representations do. Then we discussed how Takai looks like and what are the differences between the different configurations. We evaluated our intermediate representation, and in the end, I just wanted to thank you for listening, and you're also welcome to try out Opal and to check out Takai. You can find a tutorial on our website on how to use it and how to generate also the intermediate representations at different levels for a certain method only. So yeah, try it out. Thanks.
Thank you very much, Michael. I apologize for the audio-video delay. I am not entirely certain what the cause of this is. I will be switching to a different setting in the video player for the next videos in case this is on my end. Michael assures me that he tested it beforehand, so I assume that it must be on my end. I would encourage the Opal team to upload the video with synchronized video and audio to YouTube so that everyone can watch it in the intended format. Now let me stop sharing and switch back to audio and video so that we can take questions. We already have 2 questions in our chat. The first is from Manas Thakur, at IIT Mandi, India. Does Takai preserve bytecode indices, BCIs, from Java bytecode?
So at first, I also want to apologize for the terrible video delay. Sorry, I don't know what happened there. And to answer the question, no, Takai does not preserve the bytecode indices. And also, it's not possible to completely get the original bytecode out of the representation anymore once transformed.
Thank you. The next question comes from Tesla Zhang at Penn State University, and that one is, how does Takai L2's alias analysis work? She supposes that alias analysis, or he supposes that alias analysis is difficult in general, and you seem to do a simple subset of it.
Yes, so the L2 alias analysis is, as I said in the talk, based on abstract interpretation. And we also do only amassed alias analysis. So we can also only have analysis alias information when we can be really sure that a variable must be an alias of another one.
Thank you. Then we have space and time for one more question, but I don't see one right now. So I assume that that means that we are done with the questions for today. Still, thank you very much for the great talk. Apologies again about the audio. I again assume that it was something on my end here. But very good work, and still no further questions. Then let us move on to the next talk.
Yeah, thank you.
Thank you.
Trace hope.
The next talk is going to be by Raphael Monard on value and allocation sensitivity in static Python analyses.
Hi everyone, thank you for being here. This work is about an experimental evaluation of value and allocation sensitivity in static Python analysis. I'm Raphael Monard, and this is joint work with Abdelraouf Wadjaout and Antoine Minet. You can find the slides of this talk as well as additional resources on my website. So, we focus on analyzing Python programs because it's one of the most popular programming language these days. It ranks second most used language on GitHub just after JavaScript. From a PL perspective, Python is an object-oriented dynamic programming language, meaning that it has dynamic typing, so you don't have to check variable types before running the program, and actually one variable may have different types during the program runtime. You can also, as a user, redefine the behavior of most operators in custom classes, so you can change the behavior of the addition, of field accesses and index accesses and that kind of thing. You also have introspection operators allowing you to affect the control flow of programs by looking at the type or the structure of an object. You also have self-modification capabilities, meaning you can add or remove attributes dynamically to an object. And you, of course, have this eval statement. And here we're interested in performing static analysis of Python programs. And this is based on a previous work that was focusing on sound type analysis by abstract interpretation and published into this year's ECOOP. And the goal of this analysis is to detect all potential runtime errors. In Python, runtime errors are encode exceptions raising to the top level. And this is difficult for two things. The first is establishing a sound approximation of the semantics is difficult because Python is not standardized, so you have to hunt for the semantics in the documentation and the interpreter's code. And then, since users can override the behaviors of most operators, you also have to take that into account to your semantics. And then supporting a decent language and library subset is difficult because the language and the library are really big. And this also entails that being able to analyze real-world programs is really difficult. And so we've implemented this analysis into MOPSA, which is a static analysis framework being developed in our team. And the goal of this framework is to ease the development of static analysis by providing modular, reusable domains that you can then combine at your will as a user to define your own analysis. An example of this modularity is that MUPSA is able to analyze subsets of the C and the Python programming languages, and they share the same domain which performs the fixed point computation for loop analysis. In today's talk, we'll be interested in looking at 3 different research questions. The first is, what's the difference between a type or a value analysis experimental loop? So what's the cost of adding the value sensitivity, and how much precision do we gain from that? The second is, so Python is object-oriented, and we use a heap abstraction, which is called the recency abstraction. And what's the best way to abstract addresses within this recency abstraction? Does this address abstraction depends on the value sensitivity chosen by the user? And finally, is abstract garbage collection worth enabling in our setting? So, we'll first see how the type and value analysis work on a small example before moving on to the experimental evaluation. In both, type and value analysis work by induction and the syntax, and they're context and flow sensitive. So let's focus on this small example. So we define a task class having a weight attribute that must be positive. And then we define 4 different tasks and compute their average here. So when we call task of 2, the initialization method will be called. And since we only know that, since we're doing a type analysis, we only know that weight is an integer, and we don't know that weight is positive, we have to raise a potential value error here. And actually, we have to raise 4 potential value errors because they also may happen in the subsequent task creations. So at the end of line 6, what we know is L is a list of tasks, and all these tasks have a weight attribute, which is an integer in our case. Then if we continue the analysis, we're able to infer that I and M are integers. And when we're performing this L of I weight access, we have to raise a potential out of bounds index error exception, because we don't know anything about the length of the list nor the range of I. So this may access something that is out of the list for the analysis. But then we don't have to raise a potential attribute error on weight, because we know that if the list access is valid, then we'll have a task which has an integer weight, so that's fine. And at line 10, we have to raise 2 more false alarms. The first one is that since we are doing a type analysis, we don't know the length of the list, so we don't know if the for loop here will be executed. And if that's not the case, I will maybe undefined, and this will raise a name error. And we also have to take into account a potential division by 0 error. So let's now see how the value analysis would work on the same example. So the value analysis is implemented as a refinement of the type analysis. This means that, for example, during the assignment at line 4 in the call to task of 2, the type analysis infers that self.weight is an integer, and then it will dispatch the statement to the interval domain that will perform the same thing in the value analysis part. The raised value error here is never reached, because now the analysis is able to know that the weight is positive, so we remove 4 false alarms. And what we know at the end of line 6 is, so L is a list of tasks having integer weights, and their weight is between 1 and 5. We also know that the length of the list is 4. During the analysis of the loop, we're able to infer that I is between 0 included and 4 excluded, and that now L of I is a valid list access, because we know that the length of the list is 4 and that I is between 0 and 4. And at the end, we know that I is equals 3, so we can perform safely the division at line 10. So we don't have false alarms anymore in this case. So there are a few other works performing static type or value analysis of Python programs. And to the best of our knowledge, none of these analyses support both type and value analysis, and they are thus not included in our evaluation in this paper. But you can find a comparison between our tool and these tools in our ECOUP paper. So let's see now the experimental evaluation. So we use benchmarks from the Python performance repository, which are used to test the performance of their interpreter. And we also use two programs from a command line utility called PathPicker, which is developed by Facebook. And this is a slice of the articles table, so that's why, in particular, the total line corresponds to the total line of the articles table, and the numbers may not add up for this particular line. So one thing we expected and that we can notice is that the type analysis is cheaper to run than the value analysis, but it also raises more false alarms. What an interesting fact is that the number of type-related exceptions detected by the type analysis and by the value analysis is the same. And this is interesting because it means that in our benchmarks, there is no variable where its type depends on the value of another variable. And this in turn is interesting because it means that if we're only interested in in catching type-related exceptions, the type analysis is sufficient. Another interesting thing to notice is that so index errors are the number of potential index errors, false alarms here, is divided by 10 when we perform the value analysis, because we now know the length of the lists and numerical invariance, so we're able to rule out a lot of false alarms. So in conclusion, for this part, the value analysis doesn't remove false types alarm. It significantly reduces the number of index errors, and it's around 3 times costlier than the type analysis. Okay, let's switch to the recency abstraction. So the goal of the recency abstraction is to allow a precise analysis of object initialization, assuming this happens just after the allocation of an object. And this precision is usually achieved by keeping 2 abstract addresses per allocation site. So you'll keep, on the one hand, you'll have the most recent address corresponding to one concrete address where you can perform strong updates. And on the other hand, you'll have the older addresses, which will be summarized into one abstract address. And we'll see on the next slide how splitting the most recent address from the other ones keep the analysis precise. And during the evaluation we've done of the type analysis, we figured out that objects of the same type could use the same abstract address without losing too much precision and gaining some memory usage. So so we'll consider this partitioning as the first one in our recency abstraction. So let's see how this works here. Using the value analysis. So if we perform the allocation of task of 2, we'll ask the recency abstraction for the recent task address, and this is in use, so we can use it right now. During initialization, we will want to add that the weight attribute is an integer and is 2, and we'll store that by doing a strong update. Then, when we call task of 1, an interesting thing happened. During allocation, we'll ask the recency abstraction for the recent address, but this is already used here. So what the first thing that the recency abstraction does is move the recent address into the old one, giving this state. And then we can use the recent address to perform the initialization and get that state. When we call task of for, again, at a location, we ask the recency abstraction to use the recent address, and since it was used, the previously recent address here is summarized with the older addresses to get that into the weight. And then during initialization, we're able to perform a strong update and know that the weight is now full. And during the last call, we still do one merge of the previously recent address with the older ones, and we obtain this final state. And so this works quite well on that example. But we've noticed that this type-based partitioning is imprecise in some cases. For example, if you have nested for loops, the issue will summarize the previous ranges into one old address, and this in turn will mean that we'll mix the ranges for I and j. So in the case of a value analysis, performing a type-based partitioning for ranges doesn't seem to be a good idea. So what we've done is we have variable allocation policies where the user is able to choose how to abstract address of a given kind. So if you only perform type-based partitioning or type and location-based partitioning, and you can find more details about this in our paper. So let's see what. So we'll compare the two kinds of partitioning in our experimental evaluation. So as you can see, in some cases, such as Chaos or Richards, performing the type-only partitioning is extremely beneficial from a computational cost point of view, but usually type and location partitioning is a bit more precise than performing type-only partitioning. Yes, as I've said, so type-only partitioning is more efficient computationally, and it induces 9% alarm overhead. Now, let's switch to abstract garbage collection. So previously, all allocated abstract addresses were kept in the state. So, for example, in this example here, we have that these task objects are not reachable outside the call of f. So, for example, at line 6, there is no way to reach these objects. But in our analysis, these recent and old addresses would still exist after line 6. So what we've done is we've implemented a tracing abstract garbage collector, which reduces the size of the abstract state. And so we have an example in our paper where the AGC may improve the precision by collecting an old abstract address. But we've noticed that this precision improvement doesn't happen noticeably in our benchmarks in the number of false alarms we report. So in related work, the idea of using an abstract garbage collector is not new. It's been applied a lot in the analysis of higher order languages, and they've had really nice results in that field because they're able to reduce the analysis time by an order of magnitude, and they may also improve the precision. I found less references in the case of static analysis of object-oriented languages. And so in the paper type analysis for JavaScript, they have a few sentences saying that they have an abstract garbage collector. It reduces their memory usage, but doesn't improve the precision nor improves the running times. In our case, so as I've said, the precision is unchanged, but the relative time or memory improvements are noticeable, as you can see in this table. We have a global 38% analysis time improvement, 47% less memory used, and this is by spending less than, in average, 6% in our abstract garbage collector. And as I've said, there is no precision improvement. So, in conclusion, should you use types or values for your analysis? Well, it's your choice. if you only interested in type-related exceptions, as we've seen in our benchmarks, the type-only analysis would then be sufficient. But if you're interested in catching a wider ranges of exceptions, then the value analysis would be more interesting. We've seen various allocation policies for the recency abstraction, which may depend on the type or the allocation site. And we've seen that choosing the allocation policy also depends on if you're performing a type analysis or value analysis, if you want to have the best results possible. And abstract garbage collection is a no-brainer. You should just enable it, and it's really beneficial to have. In future work, it would be interesting to have dynamic allocation policies. So one way would be to automatically define the allocation policies using a pre-analysis or even during the analysis. And another thing would be being able to scale to more realistic Python applications and check that the results we've obtained in these small benchmarks still applies in the case of bigger programs. So let's finish this talk with an XKCD comic capturing, I think, what is really the essence of Python. And thank you for listening, and I'd be glad to answer any question.
Thank you very much. Now let's switch over to video discussions. There we go. Raphael, can you hear me?
Yes, can you hear me as well?
Excellent. So let's see. We don't have any questions for you yet. I'm seeing some editing happening, so we may see one in a moment. But yes, for now, perhaps, what do you currently see as the main challenges to scaling your analysis further?
It's a really good question. I think I have two main challenges. The first is being able to analyze functions modularly in order to be able to reuse the analysis we've done for one function and to scale to bigger programs. And about bigger programs, the biggest issue we have right now is supporting the standard library, which is really big. So one thing we've done is we use type annotations provided from a project called the TypeShed project. But so these are useful for the type analysis, but less useful for the value analysis.
So these type annotations, how far do they extend? And did you find them useful for all of your benchmarks, or did they only apply to the benchmarks that were actually annotated?
So they provide annotation for most of the standard library, and they're quite useful. The biggest complaint we have about them is they don't annotate the exceptions a method may raise, and this is so this reduces our soundness guarantee in our analysis when we're using these type annotations. And we're currently working on trying to sidestep these annotations and analyze ourselves the standard library. But the issue is some parts are written in C. So yeah.
Yes, that is, of course, a common problem, these analyses. Now, we have our first question here from Alan Cox, who says, this seems like a nice system. Are you going to release it anytime soon?
Oh, soon is a good answer. We don't have a definitive release date yet because we'd like to finish some things about the interface of the overall analyzer, as well as providing a bit of documentation. and we haven't had the time to do all that yet, but it should be public really soon. And if you send us an email, maybe we can give you access to the prototype, which is not really well documented right now, but should be documented in a few weeks.
Thank you. The next question comes from Tesla Zhang at Penn State University. Why aren't you doing type-based and location-based analyses at the same time? Could they conflict?
So I'm not sure I understand what's a location-based. Oh, so sorry, the location-based partitioning. So we're doing we're doing both the type-based and location-based partitioning for ranges, for example, in the value analysis. This helps us gain precision, and but they're merged together. We cannot separate them.
I see. So you run them as separate passes independently of each other and then merge the results.
No, really so this partitioning is done by the recency abstraction, and so we use both the type information and the location information, and there's no way to, and they're not performed in separate analysis.
Okay, thank you. Same person asking again, have you thought about using this framework and doing type inference on Python programs?
Yes, so that was the focus of our ECO paper. You can find it on my website if you're interested. So that was the first step, and we're doing some kind of type inference. We're also interested in alias analysis, and our end goal is to detect runtime errors, as I've said, but we're performing type inference in some sense.
Mm-hmm. Thank you. I think we have, well, technically we have a good amount of time for questions, but I will ask one more from Mehdi Bouazis. I don't know the affiliation. Could you use Mopsa's C analyzer to infer specs for the standard lib?
So that's what I'm currently working on.
Oh, okay.
So yeah, as I've said, Mopsa supports subset of C and Python analysis. And we're trying to use the C analysis and the Python analysis, but it's work in progress.
Okay, thank you very much. And then I think with that, we have had 3 very good talks on the 3 research papers submitted to SOAP. We now have a break of 24 minutes, so sufficiently long to grab a snack, stretch your legs, and do whatever else you must do in your break. Enjoy the break. We'll be back after it with our first session of tool talks, starting with Bernhard Scholz from the University of Sydney talking about Soufflé, followed by Dupe, the points to analysis that was previously mentioned. Then we have Code Checker from Ericsson, presented by Gabor Marton, and a colleague, Daniel Krupp from Ericsson. And finally, we'll be looking at Clay, presented by Christian Kadar and Martin Novak from Imperial College. See you in 23 minutes. quick audio video checks for the presenters.
Cool. Hi, Christoph. This is Daniel.
Hi, Bernard. Work well?
It works well, it seems.
Nice.
Hello, Christoph. It's Gabor.
Hi, Gabor. That works well.
It's me, Martin.
Martin, that also works.
Great. Thank you.
Daniel, I can see your video.
Yeah, video works well.
Okay. Then we're ready to start in about 3 minutes. Bernard, you will be presenting live, to my understanding.
That is correct. Yes.
Very good. Thank you for joining us so late for you.
No worries. Should I start bringing the slides up to speed so that?
Yes, you can go ahead and do that now. We still have another 2 minutes, so plenty of time.
Just a quick check, guys. Can you still hear me?
Yes, we could hear you.
All right, thanks.
It was a little quiet, but it worked.
Okay.
Bernard, we can't see any slides yet. Now we can. Thank you. Welcome back, everyone. It is just the hour in whatever, well, in most time zones that you might be in. With this, we're introducing our new format, Tool Talks, and our first presenter is going to be Bernard Scholz from the University of Sydney in Australia, talking about soufflé. Bernard?
Thanks so much, Christoph. Today, thanks so much for inviting me for this tool talk. So today I'm talking about soufflé, and soufflé has been a very long journey. So it started as a visiting professor from 2013 to 2015. And way back, the Oracle Labs in Brisbane was predominantly programming their static program analysis tools in C++. And as a consequence, the development time of these tools was quite lengthy. For a small program analysis, it was sort of calculated one and a half person years. And way back, we wanted to basically overcome these long development times. And we have been reading a lot about data log. We started to understand Yanni's work about dupe. He will present this later. And so we wanted really to use a declarative approach, a domain-specific language approach for reducing the development time of static program analysis. And the idea was to really come up with a new paradigm for evaluating data log programs to achieve basically performance which is seen in handwritten C++ code. And that was the genesis of soufflé. And so soufflé needed really some new techniques for making the evaluation fast. So we had to use heavily program specialization techniques. And these specialization techniques are based on Futamura projections. We had some early papers, a CAF paper and a CC paper, but to really make it fast like handwritten C++ code, we needed really quite a bit of database technology as well. So we had to develop highly parallel in-memory relational B trees for representing these relations in data log. We needed auto-index selection to really minimize the memory consumption and increase the speed. And we needed quite a bit of other extensions like provenance and for debugging and equivalence relations. So there was really a lot of work the last 5 years centered around Soufflé to make it useful and really fast for static program analysis applications, but also for other applications wanting to use Datalog as a domain-specific language. The history of Datalog in static program analysis goes way back. So it goes back to RAPS and Angler. They have been introducing Datalog for static program analysis problems quite in the mid-90s. And the key observation there was that Horn logic is a very natural way for expressing abstract program semantics. So in only a few lines of code, you can really express very powerful systems, and it really does not require backtracking in this Datalog semantics. So in theory, it should be, but it takes quite a bit of work to really make it fast. But let's go in more detail to a static program analysis setup. And so what we have here is an input program. It gets pushed through an extractor, and what this extractor is doing, it just really translates a program of the an input program into a relational format. The program analysis itself is expressed in form of rules, and then the output of the extractor, these are basically the input relations get then pushed into a Datalog engine like Soufflé, and then we get the output. And here for Soufflé, we really need to acknowledge that the facts may change, but the rules cannot change because they get synthesized to standalone programs. How this works is really that it's quite a complex procedure. Several stages are involved to create an executable program from a set of rules. But what we have to really ease a little bit the execution, we have an interpreter which makes the execution set up a little bit faster, but then when it's evaluating, it's slower, whereas the synthesizer is there to really create a standalone tool, a library or a program in its own right, which can then be executed very fast. Here's a small little example. I don't want to go much into detail about the semantics. I feel quite obvious, but it's a security analysis problem. It's related to Java JDK as well. You have something called the security coding guidelines. And what you want to achieve is that a vulnerable statement is protected by a protect statement. And you can express this via simple reachability analysis, where you have basically an unsafe region. So from the starting point in the control flow graph, you basically reach forward in the direction of the control flow graph, and you only propagate unsafeness if the current statement is not a protect, and the violation itself is then basically an unsafe statement which is vulnerable. And you can then really express this nicely in 3 logic rules. And I really want to demonstrate this, that this is not just an example. I really want to demonstrate this also in form of a tool. So I try to achieve this by switching to my terminal. So here I have really the same example in Soufflé. And what you can see here is that there we have a little bit more scaffolding for running this Soufflé program, or the data log specification as a program. So we need some notions of declarations of these relations. And then also we need to say that we need to read some of these relations as input. We see exactly the same rules here from the slides, and then at the end, the output. And when we run this in the interpreter, we just need to run Soufflé, which you need to install. You can either install it from scratch, going straight to the GitHub repository, or there are some pre-packaged versions of Soufflé for various operating systems. You need to install it, and then you have Soufflé running in your terminal. And if you really want to run now this analysis, what you can say vulnerable.dl, that's the security analysis, minus d minus says it really sort of should print the output on the standard output, and then I need a minus f for letting know where the facts are, and these facts are just standard fact files. And as expected, the last statement is really vulnerable because it could be a zero-trip loop. The fact files themselves, like the edge fact file, is just a tab-separated text file. And so it's quite easy to process for running Starlog programs. So I want to switch back to my presentation. So this was really just a very quick flavor of Soufflé. And there are other ways of running it using the compiled version, which will take a little bit longer. You can generate the C++ code itself for embedding it into other projects. And there are, of course, language interfaces. As in my last minute or so, I want just to highlight Soufflé is declarative, or Datalog is declarative, but it's not performance declarative. So you need to put quite a bit of effort into making Soufflé programs really fast. So you really definitely need to do the synthesis, the compilation. You also need to work very hard on your query schedule. So a lot of these rules you specify in Soufflé require .plan statements to really make it fast. And it's an art form to really get this performance. And to achieve this also, you should use profiling. So there is a profiler, and when you run it, you will notice only a handful of these rules are performance dominant, and you need to then optimize these performance dominant rules. Soufflé is really built for large scale logic oriented programming. So we have notions of components. We have recursive records. In logic programming, you might want to, is also known as terms. We have functors, so it's really a Turing equivalent machinery. We have a type system, we have signed, unsigned, float, and symbols. And there's really a cornucopia of different features, making logic programming for larger static program analysis projects much easier than using classical Datalog. There have been a huge number of projects now using Soufflé. Here's only a handful of projects. I apologize if I haven't listed all of them, but a very dominant one is the Dupe project. Yanis will talk about this later. We have OpenJDK security analysis, which we did originally at Oracle Labs. a lot of smart contract analysis. We have binary translation at Grammatech, some Haskell optimizations, and so on. So this is really my last slide. I'm already a little bit over. We have a GitHub repository. There is a lot of ongoing work in the area of scheduling, type system, union records, and incremental evaluation. And I welcome everyone to join the Soufflé community. Thanks so much for this.
Thank you very much. We have a first question by Andrew Jones, which is, how does Soufflé compare to something like CodeQL from GitHub?
I'm not so familiar with CodeQL, I have to admit. Well, first of all, Soufflé is not specific to code analysis. It has been designed for it, but you can say it's really a very basic, pure data log engine, which focuses on the fact that rules never can change, are always static, only the input, the facts may change. And so there are these inbuilt assumptions, and it's really more a language than a tool in some ways.
Thank you. We have a next question from Alan Cox about what does manual query planning let you do in Soufflé?
Okay, so the 10-minute format is a little bit tight to explain this in more detail. I wanted to explain it in more detail, but so what this really means, this dot plan statement, is that for each rule, there is a loop nest is generated, and the order of these loops is arbitrary. So any order is semantically correct, but performance-wise, it has a big impact. And the user needs now to find a good permutation to really achieve performance. And we are talking about 10x, 100x factors if a wrong predicate order in the body or wrong dot plan statements are chosen.
Thank you very much. And I think with that, we're out of time, but thank you for the very interesting talk. Unfortunately, we didn't get to hear much about what version 2.0 is going to bring in new matters. But in exchange for that, we're now going to hear Yannis Maridakis discuss with us one of the most important, as we said, dominant applications of Soufflé, namely the dupe framework.
Okay, so give me 1 second to make sure that I have correct video.
We can see you. We can no longer see you.
No, you can't see me.
Now we can see you.
Now you can. Okay, so I will talk about the dupe framework. I'll give you a quick introduction of the dupe framework. Let me share my screen, and I think it should be fine now. Oh, okay.
Yes, we can see it.
Yeah, not the right way. Screen sharing. Let me share the window instead. No, maybe not. Sorry about that. Give me a sec. Okay, so should be fine now. So I'll give you a quick presentation of the dupe framework. It's more of an advertisement of the whole framework, although we will see some command lines, so you will get to see a little bit of how to use dupe. And if you're interested, please ask me questions over the Slack channel. So just interrupt me even if you want. I'm not going to be watching the Slack channel while I'm presenting, but if you if you are a panelist, feel free to interrupt me. It's much more lively that way. So dupe is an artifact of work for over 10 years. Originally, it was the work of my postdoc, Martin Bravenboer. He created the first version, and lots of people have maintained it and enhanced it since. It is a declarative framework. It is also a representative of many other frameworks that I've worked on since basically 2008. Dupe is our foremost example of declarative static analysis. It was originally a pointer analysis framework. Now it includes many other kinds of analysis, but they all have the same basic form of value flow analysis, and pointer analysis plays a very big role. And taking dupe as an example, we've had several offshoots. So we've had another framework, Kleiser, for LLVM bitcode, and frameworks that Bernard earlier alluded to for analyzing Ethereum smart contracts like GigaHorse and MadMax. So pointer analysis, or generally any static value flow analysis, is a domain of complex mutual recursion. The main relation, the main result one wants to compute is something that we might call var points to. What values a variable may point to, or what values a variable may hold, if you want to think of constants instead of pointer variables and abstract objects. Now, as you all know, modern languages have indirect calls. They have virtual calls or first-class functions. So there's mutual recursion between constructing a call graph and computing points to information. So unless we know what value a variable can hold, we don't know what a function call will end up calling for real. So that's the dependency of call graph to points to information. And of course, the other way is a very simple dependency, because if we don't know what code we're calling, we cannot even compute the values for all variables. The same kind of mutual recursion exists between all sorts of different sub-analyses. So we can think of analyzing dynamic features of a programming language. Like in Java, we have dynamic proxies and other dynamic loading techniques. We have reflection. All of that, the best techniques that have been proposed for analyzing them are in mutual recursion with the base analysis of value flow through the program. Now, what we would like to do is encode all of these little boxes separately, but we want to have them interact as seamlessly as possible. So that's roughly the goal of dupe. And one can think of dupe in a way of holistic program analysis, to borrow the slogan of Douglas Adams's Dirk Gently, the holistic detective. Everything is connected. So dupe is not trying to do one kind of analysis, not trying to do specifically taint analysis for a specific kind of vulnerabilities. It's trying to give you an over approximation statically of everything a program can do. And it builds on the philosophy that everything is connected and everything should be modeled in parallel, but with interesting interactions. If you think of it that way, Datalog becomes a great avenue for expressing what we want to do. Datalog is a programming language that's really based on logic. It's very much logic with a little bit of computation, logic with recursion. And it's equivalent to first-order logic over finite structures. You can think of it as SQL with full recursion. If you like thinking about databases, you can think of it as Prolog without ways to construct objects, although in practice, we do construct objects in most of the Datalog variants. Dupe right now is using Souffle as its Datalog backend, as you just heard. And Souffle does allow construction of objects. So effectively, we do have a Turing-complete language, but most of everything we express, most of our algorithms are in a subset of the Turing-complete language that is equivalent to polynomial time computation. So we take inputs as tables and we combine those inputs. And for most of what we do, we have a guaranteed of polynomial time complexity. Now, Datalog as a language is strictly declarative as opposed to Prolog. So we can reorder any clauses in the body of a rule, or we can reorder the evaluation of any rules, and we are guaranteed to get the same result, maybe not in the same time, but the same result semantically. and it enforces strict guarantees of monotonicity. In a way, it is less programming and more specification. It's very much a specification language, a logic-based language, and less of a programming language. So let me give you an idea of how we express interesting static analysis algorithms in Datalog. We have the program, we have our input program. We represent it as a database. What does this mean? Well, first, we get some tables, like table alloc here and table move. And the tables encode the instructions of the original program. In Duke, we actually encode pretty much all the instructions of the original program, but many algorithms do not use most of the tables. So here we know that there is somewhere an instruction. I'm not showing identifiers for instructions. I'm just viewing the table alloc as a set. There's somewhere an instruction that assigns a new object of type A to a local variable little a. And the same for B and the same for C. And also in compiler lingo, we have assignments between temporary variables, and those are called moves. So there's somewhere an instruction that's a move instruction between B and A. Once we have encoded our program as a database, we have little declarative rules. We actually have thousands of declarative rules that express all our algorithms. And the hello world of Datalog computation, of Datalog static analysis, is a very simple transitive closure computation that combines the alloc table and the move table. Alloc gives original values to variables, and move propagates them throughout the program. So here we have two rules, and the syntax is that the rules have a head. Each rule has a head, a connective here, an arrow in Prolog style or in graphical arrow style, and then there's a head relation that's populated on every firing of the rule, and there are bodies to our rules. And the rules are evaluated by taking the body relations, which are really tables, and then joining them together. So the really interesting evaluation here is the one of the second rule. And you can think of this as a database join based on the second column of the move table and the first column of the var points to table. But logically speaking, what does this whole thing say? It says that I know that a variable has a certain value if the variable is directly gets the value at an allocation site, or recursively, a variable 2 has a value obj if I have already proven, and I don't care about how I proved that. It could have been through any of 1,000 different rules. Many are very complicated ones. But if I've already proven that variable from has value obj, and I see a move instruction from to 2, then I know that 2 also has value obj. And here we directly see the recursion that Datalog allows us to express. So with simple evaluation, evaluating the first rule, the var points to relation gets these 3 tuples that we see here, and then joining this table with that, tuple by tuple, we join this one with this one. Now we infer that A can also point to the abstract object allocated at instruction new B. And similarly, we do the same thing until fixed point, and we get the transitive closure of the whole computation. And that's the principle for computing using Datalog. And that principle, of course, we've taken it to great lengths in Duke. We have, like I said, thousands of rules that encode the semantics of complicated language features for Java. So Duke is a framework for Java bytecode analysis. The input that we accept is Java bytecode or Android bytecode primarily. We also have a Python subset right now, but it's for a special form of analysis. The core of Duke is Java or Android bytecode. Everything is declarative. It implements a very rich set of analyses. So we have analyses that satisfy all of these keywords that I'm not going to get into from the points to analysis literature. And it also supports lots of the semantic features of Java. So we model very faithfully JVM initialization, some native methods, things like reference queues, class initialization, finalization. We have a sub module for reflection analysis, all sorts of things like that. Now, to summarize, Duke makes declarative analysis real. we express highly complex algorithms that are both very powerful and very precise entirely in Datalog. We do not write Java code for the analysis core itself, only we write some connective code outside of Datalog. The core specification right now numbers close to 2,000 rules. Depending on how you count, it could also be more than 2,000 rules. And these are parameterized by a handful of rules per analysis flavor. We have lots of flavors that give you different balances of precision and scalability. And one can think of it as getting highly efficient algorithms from a logic-based specification. And we do optimize that, and one can think of it as heuristics for setting the algorithm space. One can also think of it as giving the right plan directives to Souffle. So Duke takes great pain to optimize very, very well its rule execution. So it's a demanding client of the Souffle Datalog engine you just heard about, and highly optimized in many ways. So this pretty much concludes my advertising presentation of Duke. And what I'd like to do next is just give you an idea of command lines, how you actually invoke it, and what you see when you invoke it. And I hope if someone can quickly confirm, one of the organizers, that my screen is at sufficient resolution and visible with the terminal.
I can see your screen, but you're technically pretty out of time, and we have a couple of questions. So
okay,
I think
well,
people can see that the terminal works. So
I better take questions. I will just impress you, maybe in a negative way, with the richness of command line flags. Now, this is the Duke invocation, and these are all the flags that it prompts you to give it when you invoke it. So I'll take questions.
So first question from Arlen Cox. Given the recent disassembly in Datalog work, could much of the Duke frontend be written in Datalog itself? What costs or benefits might be associated with that?
So I don't think so, because the Duke frontend does a very straightforward translation from Java bytecode to tables. That's all that the Duke frontend does. So we do use Soot, but we only use it for fact generation. So it doesn't have any complex static analysis in there. All the work on doing decompilers in Datalog tries to solve a deep static analysis problem in Datalog. So I have some work like that, the GigaHorse decompiler for Ethereum, but also there's the Grammatech work, for instance. There's also work from CMU that uses Prolog for decompilation. So there have been like 3 highly visible decompilers from ultra low level code using Datalog, all 3 of them. But they use Datalog because they try to express complicated algorithms, whereas our front end is a very dumb algorithm. It's a one-to-one mapping from bytecode instructions to tables. So I don't see any benefit in trying to move that into Datalog. There's just straightforward engineering complexity.
Thank you. We have another question, and I think just barely time for that one, from Tamas Sabo from ITEMIS and the Johannes Gutenberg University Mainz. How do you typically go about debugging your dupe analysis implementations? Some of the analyses are really complex and run on the entire JDK interprocedurally. For this reason, it is often really difficult to find a minimal example that would help debugging scenarios.
So that's true. I mean, for complicated analysis, there are not great minimal examples of input, because there's this saying, there are no small Java programs. Like the smallest Java program, if you actually track its execution, there are 7,000 classes, I think, in the JDK that get involved just for a main method that does nothing. So in that sense, debugging is really complicated, and one has to have some invariance. This is what I absolutely expect to see at this point, and I watch it very closely to see what it does. One can also create artificial examples. There are some flags here that prevent Duke from going inside the library, that say, stay out of the library, just analyze user level code. And one can create small examples. And finally, small inputs, small programs to analyze. First of all, you probably don't want to go into the library. You want a highly controlled environment. But there's the counterpart of small analysis. And for that, Duke contains a micro analysis. and that's only something like 500 or 600 lines. And that's a good analysis for experimenting with new ideas. So those would be my quick answers. But yes, certainly debugging a complex declarative implementation is non-trivial.
Thank you very much. So now that we've seen the world of Datalog in action, we switch over to the industrial side of matters by moving on to the code checker framework, which is work by Ericsson. And with that, I will switch over to a presentation by Gabor Marton and Daniel Krupp, who will also be taking questions afterwards.
We created the Code Checker project in 2013 to replace expensive commercial C and C++ static analyzer tools with a free, open source alternative. We chose analyzers from the LLVM Clang infrastructure to be the engine of the analysis. CodeChecker drives these engines and stores their results in a database so we can browse and administrate the analysis findings. I am Gabor Marton. I work in Ericsson Hungary in the CodeChecker team. We chose Clang back in 2013 because it had an up-to-date C and C++ language support. It had and still has a permissive license, so we could easily extend it to our needs. The Clang analyzer supported path-sensitive analysis. It modeled the C language quite well. We found its memory modeling pretty mature, and it had an active developer community, which is even more active now. This slide represents the architectural overview of the CodeChecker tool. There is a command line interface which drives the analysis. There are many different build systems and compilers within our company, so we provide one uniform interface for the users to analyze their projects. There are analysis options which require multi-phase analysis. These phases are executed by the command line scripts. The primarily supported analyzer engines are the AST matcher-based ClangTidy and the path-sensitive Clang static analyzer. Our team is an active contributor in these components. We continuously add new checkers and fix bugs. The results are stored in a database, and with the help of a web server, we provide dashboard functionalities. Developers can follow each step of a path-sensitive bug report. QA managers can have a good overview of the errors, including their type or severity. They can check how many reports are associated with a specific software module, or they can follow up trends about the number of new or fixed errors per release. Also, analyzer developers may gather information about suppressed checkers, and this could be really useful for them to identify false positive cases for a specific checker. CodeChecker provides integration to code review loops. In case of a new pull request, the developers can see if there is any new report introduced by their change. They either fix the new bugs, or in case of a false positive, they may be able to suppress the report. We provide the possibility to store reports from other analyzer engines as well, for example from Facebook Infer or from CPP Check. However, these analyzers must be executed manually by the users. The CodeChecker command line executes automatically only the Clang analyzers. Our main contributions to Clang were that we added cross-translation unit analysis, we added several new checkers, and we improved the report messages. The Clang analyzer was capable of doing inter-procedural analysis by the means of function inlining. This technique, however, was confined within the boundaries of one translation unit, so we added cross-translation unit analysis, which is the natural extension of the function inlining technique, but we can get the definition of a function from any other translation unit. There are many C and C++ specific checks that we have implemented. Our efforts were and are still guided by the Cert Secure Coding Guideline, which formulates security-critical rules. These are C++ iterator and container checks, or checkers related to memory access. In this slide, you can see the progress we made with the number of the passing Cert related tests over the years. Here we display the coverage of the different Cert rule groups. This is the current state with the latest Clang release, which is Clang 10. Many error reports were hard to interpret, so for elevated user experience we tried to improve the analyzer messages. This is our third contribution. Here is an example for the improved warning messages. At the left-hand side of the slide, you can see the warning report before the improvements. The right-hand side displays the improved report. In this example, there's a global variable flag, which is set to a random value in the foo function. In the bar function, we initialize the x pointer to null, and then at line 12, the flag gets a random value. At line 13, if flag is 0, then we don't call new, so x remains null. Next, at line 16, flag has a new random value, and if that is non-zero, then x is dereferenced. But that is a null pointer, so we receive the warning. In the old version, we did not display to the user that there is a value assigned to flag in the foo function, and that value actually participates in a condition later. As for the future, we plan to open source our statistical checkers, which are based on the idea if the return value of a function call is handled at 90% of the cases, then it's an error not to handle it. We would like to further refine the taint analysis capabilities of Clang. Also, we plan to implement some form of summary-based analysis. We are hoping that with summary-based analysis, we can achieve a good balance in between precision and scalability. Naive inlining can be absolutely precise, but the computing resources may be depleted easily, even with a shallow call stack. By using summaries, we plan to model complex functions with a simpler alternative. A summary could contain information about whether a function is pure or about the range of the return values. First, we'd like to make it possible to manually add summaries to the most important library functions. For example, functions from the standard C library or functions from the POSIX standard. Then the next step would be to automatically generate summaries for certain functions. For this, we are planning to reuse already available data flow frameworks in the LLVM universe. And now, Daniel is going to demonstrate the use of the tool.
Hi, I'm Daniel Krupp, a co-checker developer at Ericsson. Let us demonstrate the cross-translation and analysis feature on the open source terminal multiplexer project. First, we need to capture the compilation into a compilation database. We can use the co-checker's log facility to do that. When the logging phase finished, we can start the analysis. We switch on the cross-CU flag, and we run the analysis on 20 threads. The reports will go to the report CTU directory. The first analysis phase just finished from the two-phase analysis. After the analysis is completed, we can upload the results to the web server. We can use the co-checker store commands to do that. We'll store the run under the name tmux-ctu. After uploading the analysis results to the server, we can investigate them and compare them. The first result set is called tmux baseline, and it is without the cross-TU analysis. The analysis consists of 98 reports, contains 136 files, and completed in 44 seconds. The second is tmux-ctu run with cross-translation unit feature. It has a considerably more number of reports, 260, but also the analysis time is 3 times longer. With the co-checker diff feature, we can compare these two runs and see which are the new results in cross-translation analysis. And then you will see we have 77 new findings. Among these new findings, there are many severe errors like null pointer dereference, division by 0, or uninitialized branch. If we click on the first new finding, we will see a long backpath rendered over the source code. We also see that the bug or the problem pointed out by the analyzer is access to field window through the VL pointer, which is null. And this will cause a crash in our program. We see that the whole control flow started out from server fn.c, and then through steps, it goes through session.c, over to notify.c, and finally it ends up in command find.c. If you'd like to see an overall overview of the findings from your project, you go to the checker statistics page, and there you see which checkers found the most errors in your code. In this case, in this small project, the Clang diagnostic pointer sign checker found the most number of bugs, and the second highest number was the Unix malloc checker. As you saw, it is worth to try out the cross-translation unit analysis, because you may find severe bugs in your code at a cost of higher analysis time.
Thank you very much. So now we have the opportunity to ask Daniel Grupp and Gabor Marton about their code checker system, or generally their industrial perspective on matters related to code checking tools and their experiences with how the various tools that they've mentioned, including Clang, Tidy, and Info, might apply in practice. We already have two first questions. And the first one is from Lingua Duo, which is, were the red arrows on slide 15 to visualize the witness path for the bug?
Yes, actually, So we display their bug passes, and each of those red arrows are edges between the nodes of the bug paths.
Yeah, so they represent the control flow. Actually, Clang Static Analyzer does a symbolic execution. And then, so yeah, it is practically a witness. So it points to the programmer that how the program produces the actual error undefined behavior.
Thank you. The next question is from Andrew V. Jones. Are the kinds of errors you find richer than what Sarif supports? Could you use your visualization to display other errors if they are in Sarif format?
Yeah. Actually, we haven't compared Sarif format. We use in the code checker tool the Apple plist format, but we could also just add, I think, Sarif format. We didn't compare in detail the capabilities of Sarif, but I guess Sarif format can also display a control flow. So to an error report, it can associate a control flow as well, as far as I know.
Thank you. The next question comes from Lingua again. She asks, are the bugs only shown on a web page, or do you also have IDE integration?
We have an IDE integration to Eclipse. Yeah, sorry, Daniel, please.
Yeah, exactly. So as Gabor said, Eclipse integration is ready. And also, of course, you can display the error reports in command line or static HTML. And we're thinking about providing an LSP, so language server protocol integration. But for that, for this full control flow visualization, we may need to extend the LSP protocol itself as well.
Thank you. She asks whether you also have these arrows in Eclipse then.
Eclipse, I think not arrows, but the bug path is visualized as a tree, I think, and then you can click on the tree elements and then it will jump in the source code to the point. So it's not exactly arrows.
Okay, thank you. I think we are about done time-wise, but I would recommend you to stay tuned to listen to her later talk, where I believe she might be discussing some opportunities to speed up LSP support for your purposes. Okay. So thank you very much.
Thank you.
And with that, we move on to our next presentation, which is from Christian Kadar and Martin Nowak from Imperial College. And this one is also pre-recorded, so I will just quickly share my screen. My apologies, that was a bit too fast. There we go.
Thank you for joining this short introduction to CLI, which I'm going to give with my CLI commentator, Martin. CLI uses a technique called dynamic symbolic execution, which is essentially a technique for automatically exploring multiple paths through a program, reasoning about path feasibility using a constraint solver. You can see dynamic symbolic execution as somewhere between dynamic and static analysis. So for instance, dynamic symbolic execution, or just symbolic execution for short, can reason about all possible values on each path that it explores, something that is typically out of reach of a dynamic analysis. At the same time, symbolic execution can interact with the outside environment, for instance, with system calls and non-instrumented libraries, something that is typically out of reach for a static analysis. Symbolic execution is also a testing technique because it can generate concrete test inputs for all the paths that it explores. And in particular, this means that it can generate actual inputs, triggers any bugs that it discovers. Finally, I want to mention that dynamic symbolic execution can reason about highly complex properties because each path is encoded as a mathematical formula. And this means that it has applications beyond bug finding and test generation. For instance, it has been successfully applied to debugging, vulnerability exploitation, equivalence checking, program repair, and many more. I don't have time to say more about symbolic execution in this short talk, but if you'd like to find out more, I think a good starting point is this review article that I wrote with Kaushik Sen a few years ago for the communications of the ACM. CLI is a dynamic symbolic execution platform for LLVM bytecode, primarily targeting the C programming language. We first published on CLI in 2008 together with Daniel Dunbar, who's also the main author of the original CLI code base, and Dawson Angler. CLI incorporated the lessons that we had learned from our prior dynamic symbolic execution system called ICSI. So CLI is quite an old system. In fact, it's over a decade old now. But at the same time, I see it as quite a new system as well, because it has continuously evolved to incorporate both recent research and engineering innovations. Importantly, CLI is open source. It is available on GitHub under a liberal license. It's primarily developed nowadays in the software reliability group at Imperial College London with me and Martin as maintainers, but with many important contributions from outside our group as well. And we recently released version 2.1 this March. In terms of impact, for instance, the original CLI paper was elected into the ACM SIGOPS Hall of Fame, which is essentially a test of time award for the paper. And the paper has also received a large number of citations. What I find particularly exciting is that these citations come from many different fields, and here I mention just a few with which I'm more familiar, but there are more, which I think tells you about the applicability and relevance of dynamic symbolic execution and CLI in particular. We also maintain on the CLI website, and you can see the URL here, a list of now over 150 papers and systems that use or extend CLI in many interesting ways. And CLI has also been used and extended outside of academia by a number of companies, some of which are mentioned on this slide. So now I'm going to pass it to Martin, who's going to tell you about some of the interesting features of CLI.
Hi, and welcome. My name is Martin. How to get started with CLI? One way is to download the source code from the GitHub repository and to compile it, or to use one of the precompiled binaries which we provide with Docker. We're currently supporting a variety of different platforms: Linux, FreeBSD, and macOS X. CLI is using the LVM compiler infrastructure, and one of its major building blocks, the LVM intermediate representation, LVM-IR. To test an application, for example, which is written in C or C++, we need to compile that application into LVM-IR. One way to do that is, for example, use the Clang compiler. As CLI works on LVM-IR, we can also test applications that are written in other languages, as long as there is a compiler which is able to convert those languages into LVM-IR. After we've compiled the application, CLI can run it and each potential path for this application. For every path, CLI bit precisely models the memory and its accesses. And using a very efficient object-level copy and write schema, CLI is able to keep tens of thousands of those paths simultaneously in memory. To direct CLI to specific parts of the application, the user can use searchers. For example, from a very simple depth-first or breadth-first search, CLI also provides random searches and more sophisticated coverage-guided searches. CLI provides different solvers, which can be selected by the user, depending on the different domain the tested application is from. We're currently supporting STP and C3 mainly, and via MetaSMT, also Selector, CVC4, and Yikes is supported. Many applications also need external interaction, and CLI provides different means to handle this. For example, for the POSIX API, CLI provides already some models that allow to execute an application without invoking external system calls. Moreover, CLI also supports different libc implementations. And if needed, CLI can also handle external library and system calls. But that's not all. CLI can be easily extended. It provides different interfaces that makes it straightforward to implement new search strategies or combine with existing ones. Similar for solvers. Also, new constraint optimization strategies or caching strategies can be easily implemented and tested using the provided interfaces of CLI. Besides that, also adding new instructions or how they can be handled is straightforward. The existing POSIX implementation is not complete, but many projects that build on top of CLI showed how easy it is to extend it. CLI also supports a variety of different LVM versions, starting from the very old LVM 3.8 to the newest, most recently released version, LVM 10. This allows to combine CLI with other LVM-based projects that require a specific LVM version. Now some small advertisement. After a very successful first CLI workshop in 2018, we want to repeat this again and give the opportunity for different CLI users and developers to meet together, from research and the industry. Therefore, there will be a second International CLI workshop in April in 2021. And we would be very happy to see you there. Thank you very much for joining us today. And remember to try it out.
Thank you very much, Christian and Martin. I'll keep my fingers crossed that next year it will be possible to attend the workshop in person. Let me stop screen sharing. And with that, we have the opportunity to ask questions to Christian and Martin. There are some here already. I think they were aimed at a different talk. Here we have one that is directly aimed at you. From Tesla Zhang, Penn State University. Do you have some AGC mechanism, term taken from the Python talk earlier, to shrink the execution state? If no, do you think it's going to help?
Right. So I don't remember when the term was introduced, but As Martin already said, CLI actually one of the main contributions of CLI is to be able to maintain a large number of states in memory. And in fact, I think that's actually a good question for Martin to add to, because he recently did some work on trying to further increase the amount of sharing in states in CLI. Martin, do you want to say something about it?
Well, just to keep it quite short. So yes, there are a couple of opportunities to keep, for example, different memory objects kind of shared parts of them or sharing them between states. That makes it quite efficient and reduces the overall memory consumptions quite a lot. But there are also a couple in general. I mean, if you have a couple of states simultaneously in memory, you can share many things, and that makes it quite efficient.
Thank you. The next question that we have is from Manuel Carrasco. He says, thanks for the talk. How does CLI support concurrency?
Right. So I guess the short answer is that the mainline CLI does not support concurrency, but there are extensions of CLI. In particular, I'm thinking now of Cloud9, which added support for pthreads. For instance, and I think there is we do have like an old PR there for that in the mainline as well, but unfortunately we haven't managed to add such support. I think there is much more to do in terms of concurrency testing, but I think that's still in the research realm.
Well, yes. So, and another answer is also, I think, a more recent publication in the CAP 2020 from the guys from Aachen. They also had an extension to CLI which supports concurrent execution. But at the end, it's straightforward to implement. Also, although it's some work.
Thank you. Any other questions? I see that we've exhausted the list in the chat. Do any of the panelists want to add a question?
Right. So we realized that in 10 minutes we only had time for more of an advertising talk. So we didn't manage to cover too many technical aspects of CLI, but if you feel free also to ask things that weren't asked in the talk if you'd like to. Otherwise, we're also very happy to take more talks offline. Just send us an email.
Thank you. There's also the opportunity to continue chatting in the we have no, that's
thanks, Daniel. That's exactly reference.
Okay,
perfect,
very good. Yes, so you'll have the opportunity to continue chatting in the SOAP thread, and then can fork off as to emails or separate discussion threads as you find most effective. Otherwise, there may be some time at the end of all of our presentations, if you are going to stay up until then, to ask some more questions. But with that, I thank our previous 6 presenters very much for their very insightful presentations. And we have 19 minutes of a break, 19 and a half minutes, until our second keynote, which is going to be by Caitlin Zadowski from Google, who will talk about Beyond Code, New Signals for Static Analysis. So this is going to be another 1-hour keynote, and we very much look forward to seeing you there also. Thank you, and have a good break. We can see you, Caitlin. Very good.
Does that look good?
Yes, we can see the slides and hear you. Everything looks great.
Okay, just let me know when to start.
Yeah, we have another 3 minutes.
I also sent you an email about the Slack channel.
You should have an invitation coming in for the Slack channel.
Okay.
So that you can answer questions later. If you don't, just shoot me another email. But use the same email that you sent me the message from.
Okay.
Welcome back, everyone. And now at 20 past, whichever hour you happen to be in, it's my great pleasure to introduce our second keynote speaker, Caitlin Zadowski. Caitlin originally graduated with a BA from Colorado College, then received a PhD from UC Santa Cruz, worked for some time at MSR at Apple, and is now a software engineering manager at Google, where she manages a team of software engineers and data scientists to make data-driven decisions based on Chrome usage in the wild. I just stole that off your LinkedIn page, but it sounds like it isn't a good match with what it is that you're doing. Caitlin today is going to talk about Beyond Code, new signals for static analysis.
Thank you for that introduction. Let's see. So To start off, to reiterate, I have a PhD from UC Santa Cruz, where my interests and focus was on understanding and improving software engineering. And in particular, I was really interested in program analysis and also usability, how to make program analysis work for real developers. I've been at Google for about 8 years though. And although I started at Google working on static analysis, I am most well known for the creation of the tricorder program analysis platform that I'm going to talk a lot more about in this talk. I've also worked on a variety of developer tools teams there, including our code review tool, Critique, our internal code search and browsing tool. And then I helped found a new team focused on studying software engineer productivity. And in fact, I have edited a book called Rethinking Productivity in Software Engineering. So if you have questions about engineer productivity, I'm also happy to talk about that. And I currently manage the Chrome data team. So this is a team that owns in the wild metrics for infrastructure for collecting in the wild metrics about Chrome browser users, and also data scientists and product analysts that analyze those metrics and get insights about users. And we are actually one of the customers of the tricorder program analysis platform, which I will talk about nearer to the end of my talk. So I'm going to talk specifically about static analysis, and I wanted to refresh the definition, analyzing source code. And really, I'm going to talk about to find potential issues like bugs, anti-patterns, inefficiencies, etc. So problems in code, although you can use static analysis for other purposes. And the key distinction is that you can diagnose these problems without executing the program. But what else could we execute? So in this talk, I'm going to begin by giving a little backstory of static analysis at Google. Then I'm going to go into some specific lessons that we learned that we think are really useful for anyone trying to apply static analysis at a large organization or even a small organization. And I'm going to talk a little about our static analysis infrastructure, the infrastructure including tricorder that is used daily by most Google engineers, so really a lot of engineers all the time for a lot of code. And then I'm going to talk about something I haven't talked too much about before, which is the kinds of analyzers we ended up with. But before I get into that, I need to confess something. Most of my favorite analyzers are not very sophisticated. So I know when people talk about static analysis, they often think about kind of fancy things where you have a mathematical model of different things going on in your program and you can make a provably correct statement about something happening in the program. But really, like a lot of the analyses that tricorder has or that I've been involved in are very simple. So pattern-based, intra-procedural, inside one procedure, and just used by general developers in Google's main code base. I'm not going to be talking about verification in this talk, and the software that we are applying static analysis to is not aerospace, medical device software. But I would like to mention that some of the considerations that go into making static analysis work in this general developer's case are also important for verification as well. All right, so 6 years ago, there was a go-to fail bug, which I like because of the title in particular in SSL encryption at Apple. And essentially there is a duplicate go-to fail statement. And so everything after the second go-to fail is unreachable. And this is trivially detectable by any number of unreachable or dead code detectors. But yet none of those were applied and the vulnerability got through. So developers didn't use static analysis tools. Why not? Even before then, at Google, there was a 2 to 3 engineer team called BugBot. And the goal of this team was to apply pattern-based find bugs. This is a Java static analysis, and also other commercial static analyses to Google's code base, I think for both C++ and Java, which are 2 of the biggest languages in terms of amount of code written at Google. And the expectation is, okay, we'll apply these static analysis tools, we'll find bugs, we'll fix them, engineers will be really happy, everything will be great. And this didn't work either. All right, so I've talked about a couple times where trying to apply static analysis didn't work out how one might have thought. So let's get into the backstory. All right, so this talk is really focused on static analysis at Google. So I need to introduce a little bit about the developer workflow of most Google developers. So for most developers at Google, we work in a monolithic repository that is more than 2 billion lines of code. And that statistic was published in 2015. So I do not have a up-to-date number for the size of the code base, but I can tell you that it has not shrunk since 2015. It has increased. We use a unified distributed build system called Blaze. This is similar to the open source Bazel. And code review and testing are just standard. So basically all code that gets written at Google, it goes through code review. And one of the things that people check for in code review is adequate test coverage. However, there's no standard IDE. So people can choose which IDE to use. There is a popular internal web-based IDE that's built on top of our own custom version control system and our own custom build system and our own custom code review tool. So that's why it's not externalized. And then also people use Vim and Emacs and IntelliJ and various other options. And for most code at Google, frequent releases are the norm. So we are developing server code where it's relatively easy to push a fix because you can just release a new version of the server. You don't have to fiddle around with distributing updates to devices, for example. And every workday, there are about 50,000 code reviews that go through the code review system and the accompanying analysis infrastructure. And some of these are actually generated by robots and some of them by people. So in this environment, to make static analysis work, there's kind of two key things that sound simple, but actually encapsulates a whole lot of difficulty. So the first is scalability and the second is usability. So when I tell people kind of like what it took to make static analysis work at Google, it was really scalability and usability. All right, so what do I mean by scalability? So first of all, modern software is much larger than it used to be. So the tricorder prototype, so kind of like getting tricorder working initially on sort of first thing that we could show people, like here's something to build off of, let's see if we should staff this further. The prototype had to work on programs that were hundreds of millions of lines of code. And it had to work for tens of thousands of software engineers and tens of thousands of code reviews a day. And the other thing I want to mention about scalability is there's a few different dimensions of scalability to consider. So first, like the analyses that you're writing have to scale. So like tricorder had to scale. It had to be able to run on so many code reviews all the time and show results to all these people. But also, and to do that, we had shardable, incremental or compositional analyses. So that's kind of the techniques that people employ to make the analysis platform or analysis scale. But there's also scalability in terms of making more analyzers to run over the code base. So allowing the contributions to scale. So you don't have a bottleneck where just a couple people are writing all of the analyses. And then another side for scaling is in terms of the process. So you want to show these results to people. You don't want to have a bottleneck where you're only showing them to a subset of people. And so like tricorder hooks into this process via code review. The other key thing to make static analysis work is usability. So there is a cost-benefit trade-off when considering analysis results. So the benefit is that you can prevent, for example, a bug from entering the code base or an issue from occurring. But if you change code that's running fine, you could actually introduce a bug while fixing one, for example. There's a cost in terms of developer time if people have to look at the code review analysis results or anywhere that you show analysis results and consider whether they want to make a change to the code base. So when you think about how to increase the uptake of static analysis, you could increase the benefit, make it really clear that some analyses are really useful, but you can also think about decreasing the cost. So this is things like automated fixes, like can you make it just like one click to apply a fix that removes the problem? Also reducing false positives, so you have less time kind of trying to decide if a analysis warning is a real issue or not. And also making the workflow integration really smooth so people don't have to switch contexts, for example. All right, so let's go back to the BugBot team. That did not work out super well. So the first version of BugBot involved nightly runs over the whole code base, bug reports stored in a central database, and you could make a query to find out what kind of bugs were in this database for your project. However, people did not really use this database. It was outside the normal workflow. You had to make a query to something special, and engineers just didn't want to go out of their way to visit this. The second attempt was the BugBot team manually triaging new bugs from nightly runs. So this at least dealt with the problem of making sure that we were only highlighting kind of things that people really should fix. So they filed bug reports for the true positives, and they fixed even things that they could manually. But it became clear that this was just too labor intensive, and it wouldn't really scale well as the code base kept growing and growing. So the third integration was in code review, just like Tricorder eventually did. And BugBot was running over the find bugs over patches sent for review, and warnings were shown as comments. And this is in the previous code review tool before critique. However, users could suppress false positives and users could filter by confidence. The fact that there were false positives at all really made developers lose trust in the whole tool. And also old issues, so issues that had previously been in the code, but that were surfaced during the review were distracting. So I've mentioned the word false positives or the phrase false positives a couple times. So I want to dig into that a little bit. So with Tricorder, when we talk about false positives, we talk about something we like to call effective false positives. The key thing here is that the perception of a false positive matters. So if a developer views the result as a false positive, that's kind of really what we care about. So for example, it could be a true positive. So like your analyzer could be actually correctly highlighting a problem in the code. But if the message is too confusing for developers to actually understand what's going on or make the fix, then we still consider it an effective false positive. If it's, again, like technically correct, but it's just not important, so people don't want to make the fix, then again, it's an effective false positive. So the effective false positive rate is the sort of user perceived false positive rate by the tool. And because it's a user perceived thing, we can't really measure it exactly. So we have to measure it by proxy. You could estimate it with the fix rates, or you could also do what we do, which is actually ask people whether results are useful or not. All right, so to summarize, developers consider the cost-benefit trade-off when thinking about static analysis results. It is challenging to get developers to go out of their way to use a separate static analysis tool. And also results may be ignored when they're not actionable or understandable. I mentioned briefly, like user-based configuration is problematic because you don't get a consistent view. I'll talk more about that in a little bit. And you don't want to keep surfacing old bugs. Fixing a bug is a risky thing for code that is not changing often because you could introduce a new problem, for example. And false positives really make developers lose trust. And trust is something that, in addition to it being bad to lose trust, when you have gained trust, you can capitalize on that and take advantage of it. All right. So that's kind of the backstory of how we, this kind of state of things before the Tricorder analysis infrastructure. I'm going to talk a little bit about the lessons that we learned. So I have kind of given a talk like this or had a conversation like this several times. And I've formulated the lessons a few different ways, but this is the formulation that I like the best right now. So distilling it into 3 things. So focus on developer happiness, make static analysis a part of the core developer workflow, and empower users to contribute. So what do I mean by those? So when you really want developers to use the analysis tools, the developers are your customers. You need to track the performance of the tool and actively solicit and act on feedback so that you can really get into this virtuous cycle with developers where they tell you problems, you fix problems, you build trust, and then improve the tools at the same time. And really like focus on users feeling like they benefit from the tools that you're creating. Second, making static analysis a part of the core developer workflow. So this is going back to this cost benefit trade-off where like making smooth workflow integration really reduces the cost for people to look at and apply static analysis results. So for tricorder, the integration point that we've used is code review. And code review at Google, as I mentioned, is this sort of nice gateway because all change goes through review, but actually there are several benefits to surfacing analysis results in code review. For one thing, developers are in a change mindset. So you've written some code, you're sending out for review, you're kind of expecting feedback at that point, and you're expecting to change the code that you've written based on feedback. So if an analysis tool gives you feedback, that's the perfect point. It's also similarly a context switch point. So when we look at patterns of developer behaviors, we see that after sending code for review, developers will switch to a different task for a little while. So you have several minutes for analysis results to complete, or even longer. Another nice benefit of code review specifically is there is a peer pressure aspect, where if you show results in the review tool, the reviewer, in addition to the author, sees the analysis results. And if the author does not fix something based on an analyzer, the reviewer can say, why haven't you fixed this? Can you explain to me what's going on? And there's also this, it makes the benefits more clear in terms of saved reviewer time. It can also make it easier just to have some of the kinds of discussions you have in review by having an analyzer surface a problem instead of having the reviewer need to surface that issue. And lastly, empower users to contribute. So with tricorder, we built a program analysis ecosystem. And the key thing here that I want to emphasize is there's not really enough analysis experts. And also analysis experts are not necessarily domain experts. So at Google, we have a lot of people that are experts in a particular API or a language or some kind of configuration technique. And by allowing them to contribute, you've really expanded the space of possible analyses that you have. And also the other thing I want to mention is that a lot of engineers really love this kind of work. And also it can be very satisfying to, for example, encounter a bug, get really frustrated at the bug, and then realize that you can introduce a static analysis check so that no one else will have to deal with that bug again and not know how to deal with it. So by making it easy for developers, across the company to contribute, we've really expanded which analyzers we can show. All right, so I'm going to talk a little bit about tricorder now. So tricorder, there's a 2014 paper, and also it's discussed a lot in a 2018 TSM article if you want some more reference. It is a static analysis platform that you can plug in different analyzers and show the results in code review. And the analyzers can be written in basically any of the top languages at Google, which is Java, C++, Go, Python, and JavaScript. Tricorder is based on a microservices architecture. So you send an analyze request whenever there's a new kind of code review patch ready to analysis services along with metadata about the code change. And those analysis services run a variety of analyzers, and they use a fuse-based file system to read the files in the change, and both in the before and after the patch. And Tricorder also takes advantage of our distributed build system and the fact that we have cached build inputs and outputs that the analyzers can build off of. And Tricorder also uses, as I mentioned, feedback channels to get feedback from developers while in the review and send that back to the people that actually wrote the analyzers. And the sort of key design points in Tricorders is focusing on value to users. So making, once we had the prototype working on those, 100 million lines programs, how do we make sure that it's really useful? So this is an example of what a tricorder warning looks like in Critique's diff view. So Critique is a code review tool. So Tricorder produces these like gray boxes. So the top one, it just says you're missing a Javadoc comment. It's a lint error. And you can click on the left, please fix, or on the right, not useful. And the next one, string comparison using reference equality instead of value equality. This is an error-prone warning. I'll mention error-prone a little more in a minute. And if you notice, there is a suggested fix attached. And if you decide to show the fix, it pops up a diff view and you can apply it directly to the piece of code. This is the change author view where they can apply the diff. So by the numbers, there are currently more than 200 analyzers plugged into Tricorder. And at least 7 of those analyzers are themselves plugin systems where you have many other analyzers that plug in. There's more than 30 languages that Tricorder analyzes. And also Tricorder supports analyzers written in 5 languages kind of natively, and then others if you call it to a subprocess, for example. People apply 3,000 automated fixes every workday. And in addition to, this is just the automated fixes being applied. In addition, like people click on please fix, I think 5,000 times every workday. These statistics are from, I think 2018, published in 2020. And Tricorder analyzes more than 50,000 code reviews every workday. All right, so going back to the feedback channels, analysis results have not useful and please fix buttons. These are used by reviewers mostly, although not useful, the change authors can also click on. And the Tricorder team tracks the ratio of not useful and please fix clicks. So essentially, if there's too many not useful clicks relative to fixes being applied or people clicking on please fix, like if that ratio gets too high, then the Tricorder team disables an analyzer. The other key thing that makes this work is, this is kind of an implementation detail, but it ended up being really important. When you click not useful, it invites the user to file a bug against the analyzer author. So we've managed to kind of take the platform out of the feedback loop in order to give the analyzer author feedback directly and quickly. And then analyzer authors will change analyses based on bug reports. And we have some great examples where, for example, people were clicking on not useful a whole bunch, and then it turns out that it was just the error message that people were confused by. And when we fix the error message, that rate goes down. And remember, like if the error message is confusing, that's still an effective false positive. And so that's still a problem that you need to fix, just as bad as if the analyzer is producing a result erroneously. I just want to briefly touch on, this is kind of from 2015, so it's from a little while ago. This is one of the first C++ analyzers that we integrated into Tricorder. So it's the number of the y-axis shows the number of instances of this problem in the code base. And this is a redundant smart pointer get call in C++. And the x-axis shows time, and the vertical line is when the check to find this was introduced in tricorder. So as you can see, we sort of steadily had an increase in the number of instances in the code base. And then once we introduced the check in tricorder, instead of kind of leveling off, we see actually a drop. So people began fixing this problem in other places in their codes. This was kind of the first evidence that people were really learning from tricorder analyzers and becoming better programmers because of it. Another thing that I wanted to touch on briefly is per project customization. So I mentioned like way back in the beginning of the talk, when we were talking about BugBot team, how you could have a per user customization and hide false positives that way. And this didn't really work out. So user customization is often problematic for a variety of reasons. First of all, it gives a discrepancy between the view of the code base that a particular team has, or even like across teams. But one thing that we've seen is one person on a team will be sort of like fixing all instances of a problem, and other people on the team will actually have hidden that from their view through user customization, and they'll be like actively like introducing new problems. And that's not a great place for the team to be in, either just like in terms of team dynamics or in terms of the code base. Also, when users hide false positives, you don't find out about the false positives, so you can't fix the problem. So for example, when we first disabled user customization, we had some kind of simple like lints, like mostly style checks enabled, and previously people could suppress false positives, and we stopped allowing people to do that. And all of a sudden we got a lot of bugs filed. It's like there's all these problems, like fix the issue. One of the things we discovered was that the C++ linter was running on Objective-C files and linting them very poorly. But basically everyone that worked in Objective-C just like went to the settings and turned off lint in all their code, and then didn't see any like style suggestions anywhere. And then it wasn't until we disabled that option that we discovered this. We were able to get the C++ linter to stop running on Objective-C files and in fact add an Objective-C linter. Also, you want to make sure that a warning is kind of like seen by everyone. They have a consistent view of the system. So tricorder allows per project customization. Most analyzers are on by default, but you can additionally add extra optional analyzers. So we still have sort of a base like view that everyone at Google shares, and then this extra stuff on top of that. One thing that's kind of nice is analyzers now have the ability to start optional and then kind of graduate to on by default after you get to a point with like iterative feedback and trust built. So one example there is we had an analyzer that is showing problems in Java code, Java optional suggestions, but they're not correctness typically. They're more kind of readability, like this code would look cleaner if you made this change, this equivalent statement. And at first we thought developers would be annoyed by having this on because it's not a bug necessarily, but kind of over time, after enabling it as an optional analyzer, after iterating with feedback, like we were able to turn it on for everyone, and developers actually liked it. There's also a project called Tricium, which is tricorder for Chromium, which is an open source version of the tricorder platform that plugs into the Garrett, which is again an open source code review tool. And you can create and deploy analyzer packages, and it leverages Chromium's distributed build system, Lucy, which is also used by a few different projects. So it's another thing you may want to check out. Actually, on my current team, we use Tricium to analyze new metrics that people add to Chromium. Okay, so in addition, so it's kind of tricorder is a big thing that I worked on at Google. But there's also other integration points for static analysis. So for example, during code editing, that's also a nice point where people are in a change mindset in that they are actually actively working on a change. However, analyzers in code editing, like ideally should be very fast so they don't interfere with the sort of like read, modify, edit loop. They also need to be IDE independent to really be used consistently. One thing I do want to mention is that we have moved to a formatting model where for just kind of like stylistic changes like spacing and things like that, you can just kind of automatically format your code so you don't have a whole bunch of small comments to deal with or apply. Also during compilation is another place you can surface analysis results. I mentioned tricorder is surfaced during code review. We also have pre-submit, so basically something where you can check something before code is committed and kind of guarantee that this analysis runs or passes before you're allowed to commit something. Although I mentioned that showing results in code browsing is not always useful because it's not kind of part of this workflow necessarily. For developers, in some contexts, it is really useful. So for security issues, for example, you may have a separate security team that's reviewing all the problems. Or if you are planning a cleanup and you want to see how often a problem occurs in the code base. So compile time checking must be faster than code review checking. And one thing I do want to mention is that we don't have compiler. We've moved away from compiler warnings. We do have them in some cases, but we're moving away from them. So really just break the build. We found people ignore compiler warnings. So when we add a new static analysis to the compiler, we want it to be something that we can break the build. So ideally it's a correctness issue. It has, basically no effective false positives. And also it has to be easy to fix, because what we do is we actually remove all the existing instances in the code base. So when you have a new compile time check, you first enable it in tricorder. So this prevents backsliding, for example. You run the compiler over the entire code base, which takes about 20 minutes. Collect diffs from the suggested fixes, create a big patch, and send that out using Rosie, which is something that takes a large change for large scale changes and distributes it across the specific people that need to review it. The other thing I want to mention briefly before getting into analyzers is that there are other analysis teams at Google that are working on program analysis tools that have other flows and kind of other specific problems they're solving. So there is a 2019 FSE paper about Fudge, which is a fuzzing-based test generation tool for Google Scale. So this to speed up the process of adapting fuzzing. This tool extracts library usage patterns from clients, and we have this big code base, so a lot of library usage patterns, and turns them into fuzz targets. And then there is an automated evaluation process to go through those targets and suggest like some likely useful tests. And then humans get involved to actually vet cleanup candidates and check them into the repository. Another example of a way we're applying analyses kind of outside of this like tricorder system or tricorder workflow is Deep Dive, which is security analysis for Android apps. So this is a framework for detecting vulnerabilities and malware in Android apps that so far been involved in fixing more than 80,000 Android apps. So this is taking APKs and data from the Play Store, doing the analysis, leveraging machine learning, and then producing malware reports and vulnerability reports. And in this case, we're analyzing apps that we don't necessarily own. And so it's really like security reviewers that are involved in deciding what to do with the results. Okay, so let me talk a little bit about some of the analyzers that have sprung up since we created tricorder. So before I get too far into this, remember my confession. Most of my favorite analyzers are not very sophisticated. They are typically simple analyzers, so pattern-based, interprocedural, and they're used by general developers in Google's main code base. However, I think there's a lot of interesting ideas here, and I think that sort of considering from the sort of program analysis academic side and some of this sort of real world, practical, interesting stuff that people do with analyzers, I wonder like what we might find in that intersection. So there's a few different types that I'm going to talk about. So like finding anti-patterns, thinking about the larger context, the outputs of code, and keeping the code base in sync. So when you think about anti-patterns, like first I talked about error-prone a little bit earlier. So this is kind of a more traditional anti-pattern static analysis tool. So error-prone involves modifying Java-C to add an extra error checking pass over the AST. Checks are modular. They're written in a declarative matcher style. And it's really easy to incrementally add new checks. We've had contributors from all across the company. We've had interns contribute. It's an open source project. We have people from outside Google contribute. Checks provide suggested fixes that are structured as diffs, and they can be applied mechanically. For example, when we are adding a new error message to the Java compiler, we do that cleanup where we run Java-C over the entire code base with error-prone turn on with the new warning enabled. You can also present an error message when someone is compiling code or in tricorder. However, anti-patterns are not just for code. So another analyzer that, and most of these analyzers are not analyzers. So I was involved in error-prone, but most of these analyzers are not written by me. They're contributed by kind of arbitrary developers throughout Google. So the respectful code analyzer looks for sort of anti-patterns in the language you're using. So for example, stop referring to master versus slave processes. This is terminology that is deeply offensive to many people. And so this is really a static analysis that is affecting a social change that also is like trying to make the engineers more comfortable instead of like affecting the instead of to change the like correctness or something of the code. Another example of anti-patterns is for data, how data is stored. So at Google, we use protocol buffers extensively, which is a language neutral mechanism for serializing structured data. So if you are developing a server, that server will take protocol buffers as input and output on the RPCs it makes, for example. And there is a proto best practices analyzer, which looks at protocol buffer definitions and highlights potential issues. So for example, if something looks timey, like you are maybe creating a time field, but you don't specify the units. I mean, this is heuristic, but this is also a problem that often happens when people are specifying a proto definition. It also looks at things like potentially breaking data format changes. So for example, there are some changes that are problematic only when serialized data is stored somewhere, like in server logs. So you can enable this for your project if you know that you have that kind of situation. Another example of where anti-patterns come up pretty often is configuration. So at Google, we have many, many configuration languages and many, many contexts for configuration. So one example is a database schemalize analyzer. So database schemas can be difficult to get right. So for example, we have a few checks here, like checking that at least one admin user has read-write access, because if there is a problem with the database and you need an admin to fix it and they don't have read-write access, it's easy to not be able to deal with the issue that's come up. Another thing that this analyzer checks for is looking at potential hotspots in accessing data. So essentially, when this is a distributed database system, and if you have and the work is distributed based on the primary key, and if you have a monotonically increasing primary key, then the sort of last worker will always end up getting all the right tasks, and you'll be bottlenecked there. So there's a check to make sure that you don't have a monotonically increasing primary key. A common example of something like this you might have by accident is using a commit timestamp as your primary key. I'm going to talk a little bit about Finch experimentation configs in a bit, but that's another kind of config that we check. And lastly, I want to mention there is a tricorder configuration analyzer that makes sure that all the enabled analyzers in tricorder provide a place for filing bugs, and also make sure that when you enable an analyzer on by default, it's already been released to production. And the way that this analyzer does that is by sending an RPC to the tricorder analyzer service. So analyzers can make RPCs. I think that's like one of the big benefits of a system like tricorder is analyzers can make RPCs to a variety of places. So I'll mention just a few other examples. So we have when we import open source projects, we import them into third party, and third party, there's a code checker that checks issues with imported open source code, including that they uphold standards, like you have to have multiple owners for a open source project if you want to use it. And also it makes an RPC to a service that looks at external vulnerability feeds and tells you if there's any open security issues for the project. Another example is the missing translations analyzer. So when you are making UI changes, you have a UI string. Google is a global company, and you need to have translations to make those UI strings intelligible globally. So this analyzer generates an XML file with new and untranslated messages, and then verifies whether the entries actually have a translation. So you have an RPC to make sure the strings are actually translated. And this analyzer is configurable, so you can specify languages that you definitely need a translation for. Another example, this is kind of like a short but sweet one, is to identify broken to-dos on change lines. So you can specify to-do in code and mention someone's username. And this analyzer makes an RPC to make sure that the username actually exists, or bug ID. Another class of analyzers is looking at the outputs of code. So not looking at the running program, but looking at something at before and after the change, how big of the binary increase, how big of the size increase you have. This has ended up being important in situations where you really have to watch your size. We also, general system where you can, called the build-based config platform, where you can, for example, edit a dot file, which is a specification language for graphs, and then see the generated PNG. So you can kind of like leverage the build system to view arbitrary generated files. And another example of something you may not think about as an output is an analyzer we call on-call board. So this is analyzing the configuration for an on-call rotation. So on-call schedules are specified in a config file at Google. And when you change that file, on-call board visualizes the config changes and ensures that the rotation is balanced, so that you're not kind of accidentally increasing the number of weeks that someone is on call too much. One last category I want to mention is analyzers that work to kind of keep the code base in sync So you're analyzing one program, but you're leveraging kind of general information from the rest of the code base. So for example, we have a deleted artifact analyzer. So if you delete a source file that's referenced in other non-code places that are also in the code base, like inside some documentation files, like basically if you reference the path to this analyzer somewhere, if the path to this file somewhere, the deleted artifact analyzer will tell you. So leveraging code search to find anywhere in the code base that the path is referenced, or potentially other places as well. We also have an analyzer that allows you to specify which portions of files need to be synced together. I know it's kind of an anti-pattern to say like you have to always modify these two files together, but sometimes it happens. For example, when you have source code and a configuration and they're both needed to run something in a production environment, and you need to keep some of them in sync with each other, you have the ability to specify that with the if this and that analyzer. All right, so kind of putting this together, I want to talk about an example of an analyzer that does all these things. And this is also an analyzer that my current team uses. So Finch is Chrome's experimentation platform. So Finch configuration files specify the size of the treatment and control group on the population of people that use Chrome, the Chrome version needed to run a particular experiment. And there are many potential gotchas with sort of specifying your experiments, like forgetting to have a control group, for example. The analyzer tool, in this case, is used by the team maintaining the Finch experimentation platform. So it's really used by the code reviewers, even more so than the code authors, kind of as a check to make sure that they're reviewing for the right things. And kind of all these examples of things the analyzers do that I mentioned, like Finch does, so it finds any patterns in experiment configuration files, like not having a control group. It sends RPCs to check that you have the appropriate leadership approvals to launch your experiment. It sends RPC to the bug tracker, which is also where we track launch permissions. It analyzes the code outputs. So the Finch config and the reviewers look through the protocol buffer, and also the analyzer is leveraging that. It is keeping Finch configs in sync with Chromium testing configurations to make the way that we're doing experimentation and the way that we test on our sort of test waterfall. And to check things like that experiment names don't clash between different experiments, so that you don't have issues when you go to look at your experimental results. And it does other things too. So like there's many other kinds of things that analyzers do, such as comparing with all the other currently running experiments to identify a potential crosstalk, like when two experiments may affect the results of the other because there's too much overlap in the group assignment. So that's it. I hope you enjoyed my talk. I hope you enjoyed thinking about some of the kinds of things that static analysis tools can do that are kind of not commonly talked about, say, in the research literature. And I just want to re-emphasize the kind of 3 lessons that we learned with static analysis at Google to get developers to really use the tool. Focus on developer happiness, make static analysis a part of the core developer workflow, and empower users to contribute. And once you've done that, see what kinds of new signals that you can incorporate in your analysis tools.
Thank you very much, Caitlin, for the great talk. So we already have quite a number of questions lined up, so I think that really got people going. The first 3 questions are from the same author, so I'm going to alternate a little bit with the later questions. The first question is by Krishna Narasimhan from Technical University of Darmstadt, and he asks, how does Tricorder ensure the separation of roles between analysis expert and API expert? Or to rephrase, how much of a learning curve is it to write the extensible plugins? Is there an internal DSL?
So I guess there's an internal DSL in that there is an internal API, and an API for writing an analyzer plugin is essentially allowing a DSL, defining a DSL. You basically implement an analyzer service, and there's a service interface, and within that you get your analyzer to do stuff, and you can read the source code and read other information. I mentioned protocol buffers. There's a giant protocol buffer that includes all the metadata you might want about a change, so you can read things directly out of the change. And Google developers are often used to writing server code, so it's like writing an analyzer into writing a server. So that's easy for people. And the sort of making sure the service runs stuff is also taken care of by the tricorder team. So you can implement the service, and then the tricorder team will actually kind of run it as part of their larger like Java analyzer service. So you don't have to deal with the kind of annoying making sure that you have enough resources to run on some machines and which machines you run on type stuff. So I think based on the fact that we have hundreds of contributions from throughout the company, and we've even had interns who are kind of like second year undergrad interns come in and write analyzers. So I think like it's relatively easy to enable.
Okay, thank you. Then for the next question by Geoffrey Reedy from Sandia National Labs. Is there a strategy in Tricorder or otherwise to represent analysis findings that were previously rejected as perceived false positives that may now be accepted given user experience improvements in the analysis? So explanations.
So often when we see, so analyzers have, the category, so like error prone is the category, and then there's a subcategory for the particular type of like pattern of problem. So like all the specific checks in error prone are subcategories. So when we look at people clicking like the not useful button, for example, we're looking at not just the category, but also the subcategory. So then we can highlight, not just like block the analyzer, but like this part of the analyzer is the part that people are having a problem with. So I think often a common flow is to have a subcategory that's getting like a lot of people annoyed at it, and then to go, the analyzer writer, like you see like a bunch of bugs for this one subcategory, and then you kind of rethink like what that particular subcategory is doing and potentially fix the issue. So we've seen many times being able to just change the message, like not change the analyzer, but change the message, and having that completely change how the analysis result is viewed by developers. So we definitely do have that flow where like something at first we would want to block it because it's so annoying, but then we're able to refine the problem.
Okay, thank you. For these kinds of messages, do you have some general recommendations for people who work in program analysis? How to write good messages?
Yes, so I think the biggest thing I would say is to test them out with other people. So user evaluation is something that seems really scary, but really just getting someone else to use your tool that is not someone that's worked on the tool can make a really humongous difference. And it doesn't have to be that you like follow a protocol and have, a sort of publishable like evaluation with enough users. Like even just having a couple developers that test it out and give you feedback can make a really big difference.
Thank you. Next question again by Krishna Narasimhan. If the developers are allowed to code in whatever IDE they want, do they also get IDE integrations for the extensible static analyses, or do they need to constantly shift back between command line and browser, command line or browser to use Tricorder?
So Tricorder is mostly surfacing results in code review. So then we've sort of sidestepped that whole issue of which IDE people are using.
Thank you. The next one is by Lingwei Luo, who asks, how do you handle false positives reported by the users? Do you just suppress them or actually use them to improve the analysis? On such large-scale code bases, you can have, she imagines a machine learning based approach to filter false positives based on user feedback. Is there such an approach?
We are not using machine learning to filter false positives. Instead, right now, we're mostly refining the analyzer. So like servicing the false positive rate to the analyzer, disabling a specific part of a check if it's problematic, and kind of like making sure the analyzer, so the tricorder team is making sure that the analyzer actually does address issues.
Thank you. Next one by Anurag Agarwal. In the beginning, you mentioned allowing users to write their own static analysis rules. This must have some sort of learning curve for developers on how to write their own rules. Is the learning curve too steep, and how were you able to manage this learning curve?
So I mentioned that for a tricorder check, it's using this like RPC server interface that people are used to. However, there are also tricorder checks that are plugin systems like error-prone. And there's even, people have contributed various things to make it even easier to write analyzers. So there's a system called Refaster that I think we've published about at a workshop, which allows you to specify as just Java like code snippets, like before and after code. Here's like what this statement looks like before and after, and it will take that and generate a analysis that does that transformation and finds instances of the first and replaces with the second. So I think we're able to kind of leverage a variety of different things to make it easier for people to contribute.
Thank you. Then just a quick comment from Bill Pugh, who says, nice work, glad to see all the progress. And then we have a question from Julian Dolby from IBM Research, who asks, for making analysis part of the workflow, do you see the IDE as a good place to put analysis?
Yes and no. So the issues with the IDE are this, like you ideally want analysis results to be fast in an IDE. And you have this issue when you have people using different IDEs that you need some, language or IDE independent way to surface results. I think an IDE is a great place to surface static analysis results, but I think there's also other things that you want to surface in code reviews, like analyzers that take longer, or analyzers where you want that peer pressure aspect, because that's one of the really powerful things that code review gives you.
Thank you. Then we have one question by Marat Akin from JetBrains Research and St. Petersburg Polytech. And he says, thanks for an awesome talk. Have you ever encountered situations where the signals proposed by the devs for inclusion in Tricoder and Co were non-beneficial or wrong in some sense?
So we definitely have people enable experimental optional analyzers. So I think there's a higher bar for the on by default, but you can add something to Tricorder and then allow teams to add it to, like, in their Tricorder configuration file for their projects. And we definitely see sometimes that people will get annoyed and will rethink like whether it's a good idea or not.
Thank you. Then we have one question by Munawar Hafiz from Open Refactory. And he says, there's a difference between generating a fix and generating a fix that is human-like and can be acceptable. How complicated are the fix suggestions and how often are the suggestions accepted?
I don't know if I have off of the top of my head a statistic of like how often there's a fix suggestion versus the fix accepted. We also see people, like sometimes people will apply the fix using that flow with the apply fix button, but also sometimes people will apply the fix by incorporating it by changing the code, rewriting the code to incorporate it. I think it also depends on how narrow the problem is. So if the problem is like a portion of a line, like for example, the redundant get call on a smart pointer where the fix is just to remove the second get call and remove the .get basically, then that's something that's pretty easy to like clearly an improvement. If you get kind of more complicated problem, then it gets a lot harder to specify a fix that looks good.
Thank you. While we are technically out of time, maybe we can do 2 more minutes for 2 more questions that we just got in, if that's okay with you.
Sure.
Okay, first one is by Yoshiki Takashima from CMU, who says, it seems that there's a significant, I think, significant educational element to your project. How valuable do you think your tool will be in an educational setting?
I think potentially useful, and that's if you have specific anti-patterns you're trying to get people to avoid when writing code, you could specify them as an analysis rule. So you could imagine doing something like this for grading student programs where you look at like some, I mean, I remember from when I was a TA grading student programs, there were some problems that were just way more common than I would necessarily expect like in industry. And so you could write an analyzer that says like, whenever you're doing this kind of bad thing, like highlight it and point it out.
Thank you. Next, we have Ziheng Liu from Penn State. Since developers prefer fast checkers, what should we do to deploy, test, and improve complex techniques like context-sensitive pointer analyses and model checking?
So I think you still can have slower checkers. The code review, I think that you often have about I forget the median time to the first review, but you could have analysis results in an hour and something like that. Tricorder also, one thing I didn't mention too much is Tricorder also has intermediate status updates. So you have something, an indication in the code review tool that an analyzer is running and results will be ready soon. So like ways to make an analyzer faster by like caching intermediate results, for example.
Thank you. And there are a few more questions in the discussion thread, so people are really excited about this work, I think. So I'd encourage you to try going there and answering them in the break if you have the time. Otherwise, we have some 16 minutes now, I believe, for break time. And after that, we'll be back with our last session, which will be a few more tool talks, 3 tool talks, and finally the wrap up. So thank you very much again, Caitlin, for the great talk.
Thank you.
Time for a quick audio video test.
Hello.
Hi, Julian. Audio and video are working. Great. Thank you.
This is fine. So I'll switch it off again into my talk.
Yes, that sounds good.
Test.
Yes, we can hear you, and we can see you. Excellent.
Let's walk.
Thank you. Eric, I see you.
Hi.
Yes.
I still got my background on. Well, I guess it doesn't matter.
Excellent background. All right. Looks like audio and video works for you guys too. Thank you.
Yeah.
We will continue in 30 seconds, but before that, I'd like to invite you again to participate in the SOAP poll, which is posted at the top of the SOAP channel right after the stream URL, because it would be very helpful for the next generation of SOAP PC chairs to know what to expect and what lessons to take away from here. Thank you in advance. Next up, we have Eric Bodden and Dominic Schubert, who are going to, he's showing up as the name here. Eric Bodden and Philip Schubert as presenters for the SOOT and phaser systems. Since both of these systems are relatively closely related, yet rather different systems, we are combining their presentations and we'll have a joint Q&A session afterwards.
Yes, hello, my name is Eric Bodden, and together with Philip Schubert, we are today presenting you our static analysis frameworks, SOOT and phaser. Today, we want to talk a little bit about what we do and who else is behind these frameworks. And then we are going to present both frameworks, SOOT and phaser, side by side, talking about the general functionality, how they work internally, how you can use them as somebody from the community, and also how we want to develop these frameworks further. And you're most welcome to contribute to further development of both SOOT and phaser. So my name is Eric Bodden. I'm a professor for software engineering at Paderborn University, and also I'm heading the group on software engineering and IT security at Fraunhofer IEM, which is also located at Paderborn. And I'm here together with Philip.
Yeah, hi. Welcome also from my side. My name is Philip Schubert. I'm a PhD student of Eric's software engineering group at the Heinz-Nixdorf Institute and the Fraunhofer IEM.
And these two institutes, they sit right next side by side in Paderborn. And the main difference is basically that on the right-hand side at the Heinz-Nixdorf Institute, we're doing a bit more basic research. So here we research mostly novel algorithms and data structures when it comes to code analysis. And at Fraunhofer IEM, we are really focused on turning these tools into production-ready use. And trying them out together with industrial customers. So let me first talk a little bit about the SOOT framework. So SOOT was actually established already in 1999 by the Sable Research Group at McGill University, and that is a kind of long time ago, right? So I actually finished my high school degree back then, and if you want to remember what 1999 looks like, that's about it. Yeah, a little different from today. So 1999 was when SOOT was first conceived, and then it really became well known at PLDI 2003 when there was the first larger tutorial about it. And this here is still one of the original slides from back then. So as you can see here, back then they were still talking about compilers and programming languages such as Small Eiffel and Java and so on, which were all being transformed to Java class files. And then the idea behind SOOT was that you would be able to analyze and transform and optimize these class files. So it was a lot about ahead of time optimization. And then you could load these optimized and potentially attributed class files into sometimes even specialized virtual machines. That is not the main use of SOOT anymore. I'm still going to be talking about how this changed. But back then, that was sort of the game. Today, we have support not only for the Java platform, but also for Android. This has been there since 2011. And SOOT really has a huge user base. So the SOOT papers have more than 1,300 citations. And on GitHub, there are more than 1,400 people who apparently like the project. We have some commercial deployments. For instance, it's running as part of the largest app stores in combination with Floatroid that I will still be talking about. And it's open sourced under the LGPL license. So anybody can use it, but also anybody who is directly modifying SOOT's code is asked to contribute back these changes to the open source project. Philip.
Yeah, all right. So in 2016, we developed the Phaser framework within the SFB 901, the Collaborative Research Center on the Flight Computing. We've really wished to analyze C and C++ code, and we felt that there is not much out there which you could use for static data flow analysis, especially, which is really why we developed Phaser in the first place. And at the beginning, we pretty much implemented some IFDS IDE solvers, which allow inter-procedural data flow analysis, and then over time we built basically the framework around those solvers. We presented then the framework at a PLDI tutorial in 2018. The Phaser framework again allows for static data flow analysis, and it supports LLVM IR. In particular, C and C++, you could analyze with the Phaser framework by using the Clang compiler to produce the intermediate representation. And we nowadays also have a growing user base. We have more than 390 people who like the project on GitHub. We also have some commercial engagement by now, and Phaser is available under the very permissive MIT license. So you can pretty much use Phaser for any use case that you might have.
Thanks, Philip. Yeah, and as you will see later, a lot of the components in Phaser are really modeled to mirror some of those that we have in Suit. So we really try to provide a similar functionality here for C and C++. And one of our key motivators for doing this is also that we saw a lot of demand for C and C++ analysis in the last few years. If you want to play around with these frameworks, so for Suit, you would go to suitoss.org. It's a relatively new domain that we reserved for the tool. We have some usage documentation in the wiki. I have to say it's not always up to date. We're actually always also looking for volunteers to try out the documentation, and please let us know if something is not working for you. You can now very easily integrate all of this using Maven, so it's very easily built and included through this. We do support current Java bytecode by now, so we recently added support not just for Java 9, but up to version 14 actually. There may still a few bugs in this area, but most of the support should actually work. We also have some limited support for analyzing source code directly, but the source code front end right now is not very stable. We're currently working on this. But my current recommendation would still be, if you can, do compile source code to bytecode and analyze that instead. And then, yeah, Suit has a lot of support for code analysis, but also code transformation. So if you want, you can also instrument and optimize Java or Android bytecode this way. Philip?
All right, so for the Phaser framework, you probably wish to go to phaser.org. It's a small blog, really, where we provide useful information on the Phaser framework. And from time to time, we also publish some smaller useful articles on Phaser and how it can be used. You will find the source code on GitHub in our secure software engineering group /Phaser. There really you find all of Phaser source code. And it's also accompanied by the documentation. So we make use of the GitHub wiki, where you can find how to install it, how to obtain it, first of all, and also what you can do with it. As Eric mentioned for Suit, I mean, it pretty much also holds for Phaser. So documentation is sometimes a bit outdated. So please let us know if something doesn't work for you. We try to improve on that, of course. The Phaser project itself is built via CMake, similar to LLVM, and that's also why it integrates very well with LLVM and also with other C++ related projects. So it makes it really nice and easy to use, really. So again, it supports the C-like languages, including C and C++. You can, for instance, use the Clang compiler for that. But you could also really use every other compiler that targets the LLVM intermediate representation. And Phaser allows for static analysis, data flow analysis, so you can analyze the code, and also provides some capabilities to transform the intermediate representation.
Great. There are also some foundational papers about both frameworks. So the ones about Suit, they also date back to 99. So there's the famous CASCON paper, which has been cited many times. It actually won also a CASCON 10 years best paper award by now. So this is the first introductory paper on Suit. And then sometime later, actually Patrick Lamb and myself and a few others, we wrote a retrospective about the Suit framework, so how it evolved over time. And I think that's also an interesting read, gives you a different perspective on things. And a paper that I also often give to my students and PhD students is a technical report that you can download from the Sable website. It's on the Gimple IR and explains how it is actually being produced within Suit and what its properties are. And if you find yourself manipulating Gimple, that can be actually very useful to get some background information about. Philip?
Yeah, for the Phaser framework, you probably wish to have a look at the PLDI tutorial we gave in 2018. You can find all of its materials on phaser.org. We also published a full tool paper on the Phaser framework at TACAS 2019. That might also be very interesting for you, I guess, if you wish to get familiar with the overall framework and in its design. And also we published a small paper at SOAP 2019, Know Your Analyses, How Instrumentation Aids Understanding Static Analyses. So apparently, as it turns out, static analysis can be quite hard, especially as static analysis is usually not just one analysis, but many analyses really that are interleaving each other. And so we really used instrumentation to get some new insights and to be able to debug analyses and to optimize them. So that might also be very interesting for you.
Okay, what you see here are some of the internals that both frameworks support. And yeah, let me go through the different kinds of analyses first for Suit. So both frameworks have a 3-address code intermediate representation. So that means all the program statements are broken down into really simple atomic statements that really only perform a single operation at a time. And in Suit, this representation is called Gimple, and it's relatively high level. So to a large extent, it actually looks like Java source code, except that it doesn't have loop constructs, and instead it has gotos. And then based on Gimple, you can do a lot of analyses and transformations. So in particular, you can do call graph analysis. And there are a number of standard algorithms that Suit all supports, like CHA, RTA, VTA. Then you can also do a standard Anderson-style inclusion-based pointer analysis and use that to create a call graph. And what's also interesting and important for Android analysis that Suit directly integrates with FlowDroid. So FlowDroid is actually a taint analysis tool that we built for Android, but it is also capable of constructing a reasonably sound call graph for Android applications. So we have that support as well. And when it comes to points to analysis, like I said, there's an Anderson-style analysis, but back in 2006, we also got contributed refinement-based context-sensitive pointer analysis. So that lets you refine certain pointer information for individual pointers. That can sometimes be pretty useful. And we ourselves also published a pointer analysis algorithm called Boomerang, which is flow sensitive and context sensitive to a very large extent. And it's also demand driven, which makes it relatively efficient. And that can also be used in combination with Suit. Then on the bottom of the slide, you see a number of interprocedural data flow solvers that can all be used in combination with Suit. So These don't come with Suite directly. You have to download a separate package, but that's about it. So they link automatically with Suite and they're very easy to use. For instance, we have an implementation called Heros, which gives you an IFDS IDE implementation. We have FlowDroid as a taint analysis. And we have Ideal, which is basically an implementation of the IFDS framework that fully automatically integrates Boomerang, though, to automatically resolve pointers in a very precise way. So basically, using Ideal, you can model data flow problems very easily without having to worry at all about pointers and aliasing. So this is all taken care of for you automatically. Then the latest support that we have is synchronized pushdown systems. So this is an evolution of Ideal, I would say, which uses a special way of pushdown systems to actually gain additional speed and precision. I'll still be talking about this on the next slide. Philip?
Okay. Also, as you can see on this slide, Phaser is modeled in a very similar way to Suite. So as intermediate representation, we are using LLVM IR. It's much more low level though than GIMP. But on the other hand, it is in SSA form, which makes it also quite handy to use for performing data flow analysis on. For the most part, the Phaser framework is implemented in a very generic way using templates and interfaces, which also allows us potentially to analyze other IRs. Maybe also someone wishes to analyze IRs from GCC. That would also be perfectly fine. So you would only really need to implement the language-specific parts, for instance, the inter-procedural control flow graph, and then you can write your own data flow analysis for other IRs. In terms of call graphs, we pretty much have the same. For the points to analysis, we are currently making use of LLVM's points to infrastructure, which is unfortunately not known to be very precise, but we are currently working on that. So we plan to integrate some demand-driven analyses using synchronized push-down systems to obtain much more precise points to information, but this is currently work in progress. In terms of data flow solvers, we also have an IFDS and IDE solver implementation. We have call strings implementation, so also the inter-procedural version of the monotone framework. And we also have the weighted push-down systems by using the Wali open nested word automaton library in C++.
Yeah, and just to give you a brief hint about what these synchronized pushdown systems are about, so basically they implement combined backward analysis, which you see here at these red arrows, and forward analysis, which are these green arrows. And what's important about it is that it models actually a fully context-sensitive problem and a fully field-sensitive problem. With some limitations. So normally this is an undecidable problem. So there are some situations where we have to cut some corners, but we were able to show empirically that normally these situations where you do need to approximate, they don't really arise very often in practice. So in practice, it's actually a very precise and also efficient framework. If you want to read more about it, there's a PhD thesis by Johannes Späth about it, which I cite here, and also a paper which we recently had at Poppo. And also there will be a talk by these three people, including Tom Reps, on Saturday here at PLDI, which I also encourage you to take a look at. They also experimented a bit with this implementation. Yeah, then if you want to include these tools in your project, this is how it works. So Suite basically provides these functionalities that I talked about. And you can very easily include it using Maven, Gradle, SBT, and so on. You can use it typically as a command line tool. There are some IDE integrations, but we don't officially support them. And there's a mailing list and an issue tracker that people frequently use to notify us about questions or problems they're having with Suite.
Phaser, on the other hand, is organized as a monorepository. So once you clone it from GitHub, you obtain everything pretty much. Again, it's organized using CMake. Therefore, that means it allows usages such as libraries. So you can write your own tools, really, that use Phaser as a library, where you can just take the parts that you're interested in. You can, for instance, use the call graph functionalities if you're interested in that, or only use the points to implementations that are there. You can also use Phaser plugins. So Phaser is pluggable. So you can write your own plugins, which you then hand over to Phaser, and it will execute them on the target code. And there also exists a command line tool, which is called Phaser-LLVM, which you can use, and you can access all of Phaser's functionalities by using that command line tool. If you need any help, we have a Slack channel where a lot of bright minds are currently included. If you wish to be added to the Slack channel, just drop me an email and we'll add you.
Yeah, then one project I still want to talk about, it's called Future Suit. It's a project funded by the DFG. And its purpose you can basically see on the right-hand side. So Suit is basically a framework that evolved over 20 years, and lots of bits and pieces have been edited over time. But the architecture already had some problems in the first place, and all this adding up didn't make it any better. And so now the purpose of this project is basically to come up with a very clean new design that still gives you the same functionality, but with lots of better software engineering properties like modularity, better testability, and so on. The IR will mostly stay the same. We are doing some minor changes, but yeah, it's still going to be a variant of Suit. We hope to be able to release a first version of this probably around the end of the year. And we are also going to be conducting a little workshop with interested stakeholders in the next few weeks, probably. So if you're interested in contributing to this or learning more about the project, please let us know. And we are happy to include you.
So what are our future plans for the Phaser framework? Old dogs, new tricks. So what we are currently doing is we improve on the synchronized push-down system solvers. We try to add support for strong updates. That's something which currently does not work in the existing implementation for Java. We are also going to fine-tune all the algorithms and the technical details. Then, unfortunately, if you have to analyze C and C++ codes, this usually comes with some additional difficulties that you need to overcome. So we are also now trying to solve some C++ specific problems. And we plan to evaluate the synchronized push-down systems on larger pieces of production software as well. For the technical improvements, sorry, Eric, that was one slide too far. Yeah, no problem. For the technical improvements, we already currently completely revised the analysis model to make it more usable, easier to use, especially for beginners. And now we are currently also working on performance improvements, because for some real-world applications that we are currently analyzing using Phaser, it turns out to have some scalability issues, especially if you have analyses that really try to find interesting properties. There also we have to fine-tune a bit to make it reasonably scalable.
Thanks. So just to summarize, so static analysis is hard, and maintaining these tools is a lot of fun, but also a lot of work. So we welcome any contributions to these frameworks. So by reporting bugs, that's one way to contribute. Fixing bugs, it's even better. If you look into our repositories, you will find some bugs that are flagged with first issue. So that's really something for people to get started with. And of course, we even like it better if people contribute entire features or extensions of Phaser and Suit. And eventually, if you like, you are also most welcome to become a committer. So this is not a closed shop. We are welcome to include other people into these projects as well. And that concludes our presentation, and we are most happy to take any questions. Thank you very much.
Thank you very much, Eric and Philip. So with all these exciting developments on the SUIT and phasor side, we already have a couple of questions. You've already answered some of them, well, one of them at least. So let me just stop screen sharing so that we can see you all and give you the opportunity to now live answer some of the remaining questions. First off, we have Yitzhak Mandelbaum from Google who asks, do you know any applications of phasor to suggesting fixes? For example, could there be a reasonable integration with Clang Tidy to suggest fixes for problematic C++ code?
As far as I know, Clang Tidy operates on the abstract syntax tree. This is a piece of information that we do not directly have within phasor. In phasor, we only have the LLVM IR. But what one could try to combine those two information, so somehow making the AST information also available within phasor, and then one potentially would be able to combine those useful information, so making use of data flow information to improve the ClangD tool and to provide some fixes or some other issue reportings that can benefit really. Interesting idea. Yeah.
Thank you. Next up, we have a question from, this one's already answered. Then we have one from Anshuman Dulia at IIT Bombay. Do the various analyses in phasor and SUIT have mutually beneficial interactions?
Yeah, that's a good question. So I guess you're kind of asking whether the frameworks are integrating with one another. Right now, they are not. It would be great to be able to do this. But technically, I think it would also be very difficult. Both are quite some beasts, and they don't share the same interfaces right now. So yeah, it's not simple, and we haven't really thought about it very much. We would have to get that somewhat more.
Thank you. Then we have next up Tesla Zhang, Penn State. Do you think it's a good idea to implement the JVM code generation target of some programming language using SUIT as a replacement for currently popular tools like ASM?
Wait, I have to parse that again. Implement the code. Oh, so that...
So generate Jimple code instead of generating bytecode for Java with ASM.
Yeah. I'm not sure it would be necessary actually, because so we have a bytecode front end that takes in bytecode and generates Jimple out of it. And that is actually a fairly stable component. So that has been giving us not too much of a headache in recent years. So I'm not sure how much would be gained by actually going directly from the JVM to Jimple instead. I don't think we would gain a lot.
Okay, thank you. The question has been marked by the submitter, I think, as checked off. Very good. Then I have a question from Manas Thakur, who said that the question about a survivor guide has not been answered. That's my mistake. My apologies. Manas asked, first of all, big thanks for being behind SUIT. But minor question, is there a phasor survivor guide for SUIT users? So if I know SUIT, how to get started with phasor?
I would probably have a look at the Tucker's paper of 2019. So there you get the general idea on what it does. And also the wiki on GitHub would be quite useful, I guess.
Thank you. Then we have one question from Anshuman Dulia, IIT Bombay. Are there any plans to include analysis specification DSLs to these tools in the near future?
Yeah, so I can say for SUIT, we kind of already have this. So for specific purposes, so DSLs, like the name suggests, they are domain specific. And we have a couple of years ago released one tool that is built on top of SUIT. This tool is called CogniCrypt. And it's basically an API misuse analyzer that can find any kinds of API misuse, not only restricted to cryptography. And this actually includes an API specification language. So you can write down at a very high level what API users should look like. And then this is automatically translated into actually pretty precise and efficient analysis based on top of Suit. And we are currently teaming up with a few people to do something similar also on top of Phaser. Yes.
Thank you. I guess we can squeeze in one more question since this is our last session and we'll be running a little late. We'll have some time at the end anyway. I'll take one last question from Manu Sritaran, who asks, UC Riverside, who asks, will next generation Suit still support IR modification and code generation backends?
We will, but actually, so if you know Suit, then the way it is set up right now, you can basically modify the Jimple IR at any point in time. It's pretty wild. And this has the problem that you cannot do a lot of caching and so on. And in the future Suit, we want to do things differently. So basically, by default, you have a read-only IR, which can be cached, and therefore the static analysis as such is supposed to be rather efficient. But then we will also provide specific APIs to replace individual method bodies and so on. So you can still do it when it's required, but you will do it in a more disciplined way. And that hopefully will give you the control that you need, but it will still give you a pretty efficient static analysis in the first place.
Thank you very much. Then I think you've made very good use of the time that you had. Let me thank you for your talk and your question answers, for the answers to all the questions again. And now let's move on to Lingwei Luo, who is also at Paderborn University, and he will tell us about Magpie Bridge system for IDE integration. So I will share my screen again.
Hello everyone, I am Ling Hui, a PhD student from Paderborn University in Germany. I am happy to give a talk at SOAP about Magpie Bridge. The title already says my takeaway for you today: don't repeat yourself and use Magpie Bridge for IDE integration. You might already heard about the Language Server Protocol, known as ASP. It is an invention of Microsoft for supporting different programming languages in Visual Studio Code, and it has been widely adopted by other developer tools such as Eclipse, Sublime Text, Vim, and so on. It is used to differentiate between the client, namely the developer tool or the IDE, to the real language understanding engine behind the scene, which provides code actions such as go-to-definition, auto-completion, and so on. They put the language server protocol between such that the language server can do the language understanding independently from the client by sending JSON messages forth and back. The client can, for example, send a request to the servers saying, I am now looking at a call to a method foo at line 5:20. Please give me the location where foo is implemented. The server will then analyze the source code and send the code location of the method foo back in a response. Obviously, the language server protocol is a good idea, since a language server can talk to any IDE or editor which supports this protocol. Magpie Bridge also leverages the language server protocol, and it is a bridge between the developer tools and program analysis. It provides a default implementation of a language server, which we call the Magpie server. It handles all the server stuff one has to do every time when implementing a language server. You can save this work by using Magpie Bridge. In addition, Magpie Bridge is flexible. It provides a set of APIs such as the interfaces, analysis result, add analysis, which allow program analysis writers to run their analysis on the Magpie server. The Magpie server then converts the analysis result into JSON messages which can be understood by the developer tools. This way, analysis writers don't need to care about the implementation of the UI features or displaying the result in the IDEs anymore. They can focus on writing the analysis better. MacPyBridge provides interfaces to two different kinds of analysis. The server analysis interface is used for analysis which are written in Java. Often they use popular analysis frameworks such as Suite or Vala. For analysis which are not written in Java but have command-line interfaces, the tool analysis interface is designed for them. Next, I want to show you MacPyBridge-based CocoaNeCrypt integrated in the editor Sublime Text. CocoaNeCrypt is a Suite-based analysis which detects crypto API misuses. When I play the video, you will see it displays the warnings about crypto API misuses in the editor. And here you see the warnings, and a quick fix will be suggested and applied. Another example is the tense analysis engine of FlowDroid. Here you see it is integrated into Visual Studio Code with MacPyBridge. It detects a SQL injection, and the result, including the data flow path, is displayed in the hello message, as you can see here. For command line tools, as I said, MacPyBridge also provides a way to integrate them. Here you see the analysis result of Facebook info displayed in the web editor Gitport. Info is not written in Java, but OCaml. So MacPyBridge is a reusable framework, and it provides reusable project services. In order to do whole program analysis, analysis writers have to resolve project scope to find the source code path, the library code path. Usually they have to do it every time for every analysis, which is again repeated work. Project services provided by MacPyBridge leverage popular build tools such as Maven and Gradle to solve this problem and save your work, since the resolution is always the same for the same kind of projects. MacPyBridge provides a few implementations which can be chosen by analysis writers. Now I explain how it works. Once the IDE sends the ASP message initialized with the project URI to the MacPy server, MacPyBridge's built-in project services can use this information to resolve the scope of the working project. Computed source code path, library code path, class path can then be used by the analysis. Currently, we already have project services for Java projects, Android projects, and NPM projects. Of course, you are welcome to contribute one and share it with us. The way MacPy server allows analysis to detect issues is instant. It triggers the analysis automatically based on user interactions reflected in the ASP notification sent from the IDE. For example, it can be configured to run the analysis when the user opens a source code file in the IDE, or when the user makes changes to a file, or when the user saves a file. The client which supports ASP provides rich IDE features for diagnostics sent by the MacPy server. You can have markers with different severities, error warning or information, or as you have seen the example for FlowDroid, the witness path for the vulnerabilities is displayed in the hello message. Or some advanced features such as quick fix, as you have seen for CocoaNeCrypt. Since the first release of MacPyBridge after eco paper, we received questions about if MacPyBridge can allow more user control. Some people would like to let the user to control the timing when the analysis should be triggered, or even allow interactions between the user and the analysis. The others would like to allow users or developers to configure the analysis by themselves. Now MacPyBridge can fulfill these wishes. MacPyBridge leverages not only ASP, but also the fact that every computer has a default web browser installed, and we extended the Magpie server to also talk with web browsers in HTTP. The way how it works is as follows. When the Magpie server is started, it will also open a URL in the default web browser. The web browser will show the configuration page for the analysis. This page is generated by the Magpie server from the configuration options and actions defined by the analysis writers through the get configuration options and get configured actions method defined in the analysis interface. The configuration options are displayed in form of checkboxes or input fields, and the actions are in form of buttons. The users can then select the configuration options in this page and submit them back to the server. The Magpie server can then use this information to configure the analysis which has been defined by the analysis writers in the configure method. Afterwards, the user can perform an action in this web page such as run analysis. This action request will be then sent back to the server. The server executes the corresponding runnable task defined for this action in the analysis interface. The analysis will be then triggered. The Facebook Info integration actually uses this feature of Magpie Bridge. So I want to note here, handling all these back and forth interactions between the Magpie server and the web browser is already implemented in Magpie Bridge. As an analysis writer, you just need to define the configuration options and actions within the analysis interface. I hope now you are interested in Magpie Bridge. If you want to try Magpie Bridge, you can visit our GitHub repository. There you can find tutorials and examples of all these tools I have shown you today. Thank you.
Thank you very much. So let me switch to video now. Thank you, Lingwei. Now let's see what people have asked about your presentation. We have no questions. Yeah, we have our first question here from Tesla Zhang, Penn State. Speaking of the interaction with IDEs, since different IDEs have their own UI frameworks with different functionalities, are you supporting a common subset among all of them?
Yes, basically what we support now is focus mostly on diagnostics and code actions. So basically you can show in these warnings in IDEs and have code actions like open a URL, a web page, or quick fixes, something like that.
Thank you. We have another question from Xixin Wang, SUS Tech. What is the essential difference between server analysis and tool analysis? Why are they handled differently?
The server analysis basically for analysis which are written in Java because Magpie Bridge is written in Java. So and for tool analysis is that we designed it for command line tools because they're not written in Java. We have to define interfaces which basically start a new process which runs the command line tools and cache the result. For example, Facebook Info, it reports a JSON result, right? We have also defined interface, which makes it easier for analysis writers to do the integration. Sorry, I can't hear you.
My apologies, my mistake. Yes. Next question is again from Tesla Zhang. Is Magpie Bridge itself extensible? Like, can we make a plugin for it to support a new IDE or a new language server protocol without, I'm not sure what new language server protocol is, without modifying itself?
Yeah, we tried to make Magpie Bridge as a framework, so it is extensible. And I'm not sure what you mean a new SP. Yeah, you can extend the language server protocol by defining new notifications, new messages. And this have been reflected on Magpie Bridge. So the Magpie server, it implements a few messages which supported by the current language server protocol. But if you wanna your IDEs or the analysis to have more functionality, which requires you to extend the SP, adding a new message, then you have to implement that from both sides. So at the MacPy server side, you have to allow the server to accept this kind of message. And from the IDE side, you have also to implement all these UI features which for this extension.
Yeah. Thank you. I guess we would have time for one more question if there is one. I don't see one now. Maybe one quick question about the language server protocol. So this one keeps evolving, to my understanding, semi-rapidly. So I'm wondering, is the trajectory that it's evolving in something that supports your activities, or do you think that there are things you'd like to do that don't seem to mesh with the intentions of the language server protocol designers?
Sorry, can you repeat your question? What do you mean?
The question is, the language server protocol keeps evolving and changing. And do you think that the way in which it is changing is in line with what you would like to see as far as IDE functionality for visualization and interaction is concerned? Or do you think that they're going in the wrong direction from your perspective?
Okay, actually, I see that what they have done, for example, the newest version of language server protocol also support progress bar. I had done some user study before. People say, okay, your analysis is slow. I would like to know how long it will take, right? I would like to have a progress bar for that. And they are definitely doing something in the right direction, but because it is a community effort, so this features is, for example, not supported by many other IDE or editors except Visual Studio Code. And also, the reason why I have extended MacPy Bridge to support HTTP is also based on the reason that I don't wanna do anything on the client side. So I just, okay, I have it as a web application and I can decouple it from that. So based on what they have done, then I can just for browser, right? A web browser, and I just have to do it once. I don't need to keep up with all these clients and asking them to support this and that. So there was definitely a thought as I was thinking about, okay, maybe I can ask them to support this language or a new feature or whatever. But then I think, okay, this is a community and there are so many IDEs and editors, probably it will take a year or 2 years until they support my new SP message. So yeah, that's the bad side of the language server protocol, that it takes time. But I definitely think this is the future and this is the way to go. Thank you.
Now, I don't want to delay Julian's talk too much, but there is one question that I think could be fairly quick. That is by Mahir Asef Kabir Mahir Kabir, Virginia Tech. Sorry, I misread. Does it support partial code analysis, or does it need to build a call graph for its analysis?
This is actually not the part of MacPy Bridge, but your analysis itself, right? If your analysis is based on Suite or Vala, they have all this call graph algorithm. So basically, MacPy Bridge can also give you information about what code has been changed. For example, if you are doing very local analysis, which doesn't require sophisticated interprocedure analysis, basically you can also do partial code analysis.
Thank you very much. And thanks again for the talk and the answers. Then next up, we have our final talk, which is Julian Dolby talking about the Vala system in relation to taint analysis. Let me share my screen with you. And now we can let Julian speak for himself.
Hello, I'm Julian Dolby from IBM Research, and I'm here to tell you about Vala using GNU taint analysis. In Chinese mythology, GNU is a weaver goddess, and GNU taint analysis is going to weave together different IDEs, languages, and analysis components for taint analysis. In the legends, GNU was a user of the MagPy Bridge, and GNU taint analysis is going to use MagPy Bridge as well. Rather than define taint analysis for SOAP, I'm simply going to go through some examples, and the first one is a Flask app written in Python, shown here in VS Code. The first thing the Flask app does is it reads the suggestion field from its request, And that is a source of tainted data because that's user input, and that's why it's shown with a yellow underscore. That tainted data request parameter is now passed to the inner and outer functions, which do some minor processing on them and return them. That's all shown with blue underscores because it's a tainted flow. And then that all part goes to subprocess.call there, which is where the data escapes the real world, hence it's a tainted sink. And so that is shown with a red underscore. Note that just above is another call to subprocess.call there. It even uses the same inner and outer functions to process its data, but it is passed a self-isolating string. So it is not and should not be shown as tainted. Note that this requires a little bit of context-sensitive data flow analysis to understand which call is actually tainted. The next example is HTML and Sublime. In this case, our tainted source is document.url, shown there on line 16, marked with a green underscore. That is then passed to the ID method, which is shown on line 6 there, just returns the same thing, which is then assigned to text and passed to document.write, where it's escapes to the web page, hence that is our tainted sink, and that so it's shown with a red underscore. Note there's another call there on line 19 to ID, but that's not a URL, so it should not be shown as tainted. And it has the same requirements for context-sensitive analysis as the Python example. Further note that the code that you see is actually in multiple script tags, and so the system must be able to assemble all of the JavaScript together in a sensible way to analyze it. And then note also that the first call on line 16 there uses the JavaScript function.call idiom, so the system needs to be able to understand at least that much JavaScript semantics. The next example is Android Java in Atom. This is an example from DroidBench. And particularly, you see a tainted sink at the top of the screen there, send text message where data clearly escapes the real world. It is passed test1.method sub b, and that calls the method on line 38 there, which calls a.f on its argument. We have enough type analysis in this example to understand that the call is to the method there in class B rather than class A. So we see our tainted source there, manager.get device ID. We return there on line 51, we return that to line 38 again, and then that gets returned to the tainted sink. Note that we need enough analysis to tell us that we're going to B and not A to get the tainted information correct. But maybe you don't want to use any of these new editors. It's also possible to use Emacs, and in this case I'm showing you JavaScript code, plain JavaScript this time, in Emacs. This is code you might see in Node.js, for example, although I'm using the same JavaScript code as last time, except that I added one more tainted source here in ID3 per call. But to have the same analysis issues with understanding the reflective call and the context sensitivity required to tell which of these three calls is actually a tainted source. Note the labels you see on the edge there, the bottom of the screen. You have tainted flow step, tainted source, and tainted sink. Keep those in mind, they will come back. So I've tried to sketch a somewhat large space here. I showed you several IDEs, and of course there are many more. And I showed you several popular languages for taint analysis. And I tried to sketch some needs like context sensitivity to suggest, and type inference to suggest that the analysis needs some amount of machinery. But are we really going to build an analysis infrastructure with all the needed machinery for each of the languages we want to analyze, and then somehow integrate each of those into our IDEs? In a word, no. GNU is going to weave it all together. We have already seen from Linghui how we can use Magpie Bridge to support a variety of IDEs, and now we are going to see how to use the cross-language analysis framework Walla to analyze all of the different languages together. Walla was originally from IBM, and it's our cross-language framework. And in our case, it works by starting from existing tools to process source languages, which it converts into its common abstract syntax tree, or cast system. Once we have cast for a program, it is then converted into a more traditional IR that consists of control flow graphs, SSA, and the like. Once we have a traditional IR, the core with IFDS, program dependence graph, system dependence graph, call graphs, and more can operate on all of those IR languages together, and it's all supported by a rich set of utilities, including a graph. In particular, we are going to use graph reachability to do taint analysis. We start with a graph there. That's Waller's graph idiom, called G. And then once we have the graph, the first thing we do is we walk across the nodes of the graph to see which ones are endpoints, are sources of tainted data. For each one that's a source, we create a BFS for Pathfinder, which is Waller's utility for looking for shortest paths across a graph, looking for paths that flow to sinks of tainted data. As we find such paths, we gather them into a list and return them. So we're going to use graph reachability, but of course we need a graph. And this is a driver. This is a piece of code that would be called potentially by a Magpie bridge. And the first thing we need to do is make a call graph builder. The AST SSA propagation call graph builder is Waller's abstract class that represents call graph builders for all the different languages we support. So this piece of code is going to be completely cross-language, although make builder will obviously be specified per language. Once we have the builder, we build the call graph, and then we build a system dependence graph, or SDG. That's a graph of statements, where statement is the idiom for Waller's IR nodes in an SDG. The graph is completely language neutral, except for any specialization of modref needed by a particular language. Once we have the SDG, that is what we give to the graph reachability code on the previous slide, along with the source finder and sink finder that we need, and that gives us all the paths we need, and then we'll see what to do with them next. But let's look at the components of this system. The first thing we needed was a source finder. In this case, we're looking for the sources are normal statements, and in particular, they're normal statements. They're read statements reading a field called URL. Remember that in JavaScript, document.url was our tainted source. The sink finder is looking for param callee, which is the Waller idiom for arguments to methods in the SDG. And in particular, it's looking for arguments to the method document.prototype.write, which is our tainted sink. In this case, Waller has a lot of support for modref of all the different languages we support, and so we can just use the standard JavaScript one without any further requirements. But those are those components we need, but I had said before, we also need a call graph. And if we're going to support multiple languages, we clearly need different call graph builders for the different languages. I'm going to start with the HTML one. In this case, what we do is we get one file from Magpie Bridge, which will be the web page that we are analyzing. And then we pass it to the HTML CG builder in Waller, which basically takes a web page, extracts the JavaScript code, builds a model of the DOM, analyzes the entire thing, and returns it. So that's where we got our path. But now we have the paths, what do we do with it? Well, for each path, what we do is we go through each node in the path, each step along the way, and we create an analysis result object for it. These you saw these before in the English talk. This is how we communicate the results of the analysis back to Magpie Bridge. And for each step in the path, we're simply computing those messages that you had seen on the slides: tainted sink, tainted source, and tainted flow step. That's where this is the code that produces the messages that you saw on those screenshots. And with that, you see the whole thing, how we can take our programs and do taint analysis across all of them, and no language in a systems independent sort of way. And with that, I've come to the end of the presentation. Thank you. I hope you have seen how we can use GNU to weave together all the different IDEs, languages, and analysis components to build taint analysis. Check out the websites, and where you can see all of the code that makes all of this beyond what I showed you on these slides. With that, thank you for your attention.
Thank you very much, Julian, for closing with a talk that weaves together many of the discussions that we've had before. And yet, of course, we now have the opportunity to ask Julian a couple of questions before we go to our closing and the announcement of the Best Presentation Award for the three scientific papers. But let's start with questions for Julian and or for Waller. Does anyone have any questions to pose? So I'm not seeing any concrete questions yet. Let's give it a minute. maybe I can ask you a question. So the CAST framework that you have for taking in input for different languages, what assumptions does it make about the language? Or put another way, what languages would be very difficult for you to support if I now wanted to go ahead and support them?
Can you hear me?
Yes, we can hear you now.
Okay, good. We mostly have worked on what I would loosely call Java-like languages. Well, not really Java-like. Python, JavaScript, Java have been the language we've used the most. We also are using HTML, but basically any language that can generate a reasonably normal, conventional-looking abstract syntax tree where you'll have statements of different kinds. It could be functional, it could be imperative, it could be object-oriented, it could be whatever. You have methods, you might typically have classes or functions, that sort of thing. Any language that is broadly in that class. And also any language, ideally what we use is languages for which there's an existing tool that gives us some form of AST that we can then convert to CAST fairly easily.
Okay, that sounds fairly general. Thank you. Then we have two audience questions. Manas Thakur from IIT Mandi says, nice talk. Does Wala handle reflection in Java programs?
So the short answer is yes. So then let me give you a slightly longer answer, which is, in general, handling reflection is an open-ended and not very solvable problem. That is, if I read a string from standard input and I pass it to class.forename, there is nothing in the code that gives me any insight about what that string is, although we do several things. There's a bunch of analysis that when we have processing done to strings, we may have some estimate of what the string is. We can sometimes use that. The other thing we've taken other approaches where, for instance, someone uses reflection. They usually then take the type, the thing they created, and they cast it to some type. We have a mode where you assume that those sorts of casts succeed, and from that you infer the kinds of types you must have created. And we have support for things like if you have a class and you call get method on it, if those strings are reasonably constant, then we can figure out what the method is, right? Basically, anytime we have static information we can use, there's typically a way to use it. Although, of course, there's nothing you can do sometimes.
Thank you. Next question is Ansuman Dulia, IIT Bombay. How does Wala assist in defining taint sources, taint sinks, and so on in a language/application independent way?
Okay, so let's step back a moment. So there's a level in which it doesn't make a lot of sense to define a taint source in a language independent way, because the kinds of constructs that are your sources are somewhat dependent on your language. So if you remember from my slide with the source finder and the sink finder, that was basically looking at the system dependence graph and just asking, is this a statement that reads document.url? So that is the kind of sink and source that we support. And that is we actually use exactly the same interface there. That was JavaScript you saw, but Python and Java are exactly the same interface, although obviously the particular functions are different. In Flask, subprocess.call was a sink. And in JavaScript, it was document.prototype.write. But they're both function calls, and in both cases, you're looking for arguments to those function calls. And so to that extent, the sink definition is exactly the same.
Thank you. Then we have Joana Cecilia da Silva Santos from Rochester Institute of Technology. For Java applications, does Wala have a way to handle the program's dependencies, for instance, by supporting pom.xml files directly?
So Wala typically works by being given a program scope. Now, we just heard in Ninghui's talk how Magpie Bridge project services are particularly able to handle pom.xml and extract the dependencies. So in that case, what would happen is that code would give from the IDE, it would find the POM XML, it would figure out what the scope is, and it would hand all of that information to Walla, which would then build a program scope out of it. So the short answer is Walla itself expects a program graph, a program scope to be defined, but tools like Magpie Bridge, on which I also work, can assemble one for you for many popular kinds of things like Maven, Gradle, Eclipse, that sort of thing.
Thank you very much. That seems to be the extent of the question so far. Then, Julian, thank you again for the talk and for answering the various and varied questions.
Inviting me.
And with that, we have reached the end of our final talk, but we still have a bit of time left here. So I would like to now give an opportunity to ask any additional questions that you might have. So what I'm going to do now is I'm going to create another thread on the Slack channel. And in this thread, you can now add any questions that you would like to ask to any of our remaining panelists, which are Eric, Julian, Lingue, Michael, Philip, and Yanis. So if you want to ask something now, feel free to do so. In the meantime, I will go ahead and present to you the presentation that we've decided to be the recipient of this year's Best Presentation Award at SOAP. The traditional SOAP Best Presentation Award is usually handed out in person, but of course this year we can't do this. Paddy and I discussed behind the scenes a little bit, factoring in the insights from the program committee, and we concluded that this year, even though all the talks were very good, we should give the award to Value and Allocation Sensitivities in Static Python Analyses by Raphaël Monard, Abdelarouf Oujaout, and Antoine Minet. So thank you very much to these authors for their SOAP award. Here see the pieces of SOAP that they have won and which we'll be shipping to them as soon as we know where to ship them to. And with that, let's see if there are any remaining questions. And yes, applause is of course a very challenging thing to do in this situation, but let's in our minds applaud the authors for their excellent work. So do we have any remaining questions from anyone? Otherwise, I would like to remind you that we have a poll going on, which will influence greatly what, or may influence greatly what the PC chairs of the next SOAP are going to do. I'm just going to repeat in the channel again. So we would greatly appreciate it if you could take a minute, or I don't think it takes more than a minute, to fill out this poll to give us some information about yourselves and how you perceive SOAP and how you previously perceived SOAP. So I see no further questions here, in which case I think I will just thank all of our speakers again and thank all of you for attending. I hope that we're going to see you next year at SOAP 2021. And thanks again to Paddy, of course, who had to leave us a bit early because it is very, very late in Australia, or almost early again, to my understanding. Thank you to Peter O'Hearn for his excellent keynote. The technical problems that had to be overcome were non-trivial, of course, but he managed to do it and get all of the key insights through to us. Then thank you to Sivu for explaining bug provenance with trace witnesses, Michael Reif for explaining Takai, an intermediate representation based on abstract interpretation, Raphaël Monard for value and allocation sensitivities in static Python analyses, and our tool talk speakers. Let's first thank Caitlin again for her keynote Beyond Code, New Signals for Static Analysis, And now finally, our tool talk presenters, Bernhard Scholz with Soufflé, Yannis Maragdakis for Dupe, Gabor Marton and Daniel Krupp with Code Checker, Christian Kadar and Martin Nowak with Klee, Eric Bodden and Philip Schubert with Suit and Phaser, Ling Luo for Magpie Bridge, and Julian Dolby finally for Walla. Thank you again, and I hope to see you again at some point in the future at one or the other SOAP.
And thank you, Christoph, for organizing all of this.
You're very welcome.
Yeah, it was great. Thanks a lot.
Take care, everyone. Congratulations, Christoph. Thank you.